The worst-case scenario for 3i Atlas sounds insane until you consider this. What if it's not leaving? October 29th, 2025. Mark that date. Circle it. Remember it. On that day, 3i Atlas will reach perihelion, the closest point in its trajectory to our Sun. NASA says it's harmless. The European Space Agency agrees. Every major observatory tracking this interstellar visitor has concluded the same thing: there's nothing to worry about. It's just another cosmic wanderer passing through our neighborhood, a frozen relic from beyond our solar system that will swing around our star and disappear back into the darkness from which it came. But what if they're measuring the wrong things? Tonight, we're not talking about collision scenarios. We're not discussing apocalyptic impacts or gravitational disruptions. Those calculations are straightforward, predictable, comforting in their certainty. The math doesn't support catastrophe in that sense. 3i Atlas won't crash into Earth. It won't knock planets out of alignment. It won't trigger solar flares or disrupt satellite networks through its mere passage. The worst-case scenarios worth exploring are far more subtle than that. What if the threat isn't physical impact, but philosophical disruption? What if October 29th, 2025 doesn't bring destruction but revelation? What if this comet racing toward us at over 130,000 miles per hour from the depths of interstellar space carries implications that could fundamentally alter how humanity views its place in the cosmos? Consider the timeline. Right now, as you watch this, 3i Atlas is closing the distance. Every second that passes brings it roughly 36 miles closer to perihelion. Observatories across the globe are tracking its approach with unprecedented precision. The Hubble Space Telescope has captured its light. The James Webb Space Telescope has analyzed its molecular composition. Ground-based facilities from Chile to Hawaii have plotted its trajectory with extraordinary accuracy. And yet, for all this observation, for all this technological surveillance, we're about to enter a period of enforced blindness. Between October 21st and early December 2025, 3i Atlas will pass through solar conjunction, meaning it will be positioned too close to the Sun from Earth's perspective for safe observation. During those critical weeks, during the very period when it reaches perihelion and potentially undergoes its most dramatic transformations, we simply cannot watch it. Think about that for a moment. The most sophisticated civilization ever to exist on this planet, equipped with instruments that can peer back to the dawn of time itself, will be functionally blind to an interstellar object during the most critical phase of its passage through our solar system. The official position is clear and scientifically sound. 3i Atlas is a comet. Its behavior matches expected parameters. Its outgassing patterns, while somewhat unusual, fall within acceptable ranges for objects formed in different stellar environments. The chemical signatures detected by JWST, dominated by carbon dioxide rather than water, simply indicate formation conditions unlike those in our solar system. Nothing about 3i Atlas, according to mainstream astronomy, suggests anything other than a natural phenomenon. But worst-case scenarios aren't about what's probable. They're about what's possible within the boundaries of our current understanding, and just beyond those boundaries where certainty gives way to speculation. So let me pose the question differently. What is the worst thing 3i Atlas could be? Given what we know and what we don't know, what scenarios, however unlikely, should we at least consider before this visitor disappears back into the cosmic ocean? The worst case isn't that it's dangerous. The worst case is that it's important, and we're not prepared to recognize that importance. The worst case is that it represents a form of contact we've never imagined and have no protocols to address. The worst case is that October 29th, 2025 could mark a watershed moment in human history, and we might not even realize it until the object is already receding into the darkness. Impossible to recall, impossible to study further. Humanity has spent decades preparing for alien contact scenarios. SETI has established protocols. The United Nations has committees. We've drafted responses and established hierarchies of decision-making authority. But all of those preparations assume certain forms of contact: radio signals, visible spacecraft, deliberate communication attempts. They assume that if intelligence reaches us, it will announce itself clearly, unambiguously, in ways we can recognize and respond to with our current frameworks. 3i Atlas fits none of those assumptions. It looks natural. It behaves mostly naturally. And that might be precisely the point. The worst-case scenario isn't an alien invasion fleet. It's something far more unsettling. A visitor that could be entirely natural or carefully designed to appear that way, and we lack the capability to distinguish between those possibilities with certainty. Tonight, we'll venture into the speculative shadows that mainstream science appropriately avoids. We'll explore scenarios that begin with established facts and extend into territory that might seem like science fiction, but remains tethered to actual observations and real measurements. We'll ask questions that make astronomers uncomfortable, not because the questions lack merit, but because the answers, if they exist, lie beyond our current ability to obtain them. This isn't about conspiracy theories or unfounded panic. This is about intellectual honesty regarding the limits of our knowledge. This is about acknowledging that when an object arrives from interstellar space formed under completely alien conditions, carrying chemical signatures unlike anything in our solar system, approaching at velocities that dwarf our fastest spacecraft, we should at least consider the full spectrum of possibilities before filing it away as just another space rock. 3. Atlas will make its closest approach to the Sun in 356 days. Then it will begin the long acceleration outward, gaining speed as it climbs away from our star's gravity well. Within a few years, it will be beyond the orbit of Neptune. Within a decade, it will be farther from the Sun than the Voyager probes, those tiny artifacts of human ambition that have been traveling for nearly half a century. And if we've misunderstood what 3i Atlas represents, if we've failed to recognize something crucial in its composition or behavior or purpose, we'll have lost our only opportunity to investigate further. There are no do-overs with interstellar objects, no second chances, no ability to recall them for additional study. They arrive unannounced, pass through on hyperbolic trajectories that guarantee they'll never return, and leave us with whatever data we managed to collect during their brief transit. So before 3i Atlas makes that perihelion passage, before it disappears behind the solar glare, before we lose sight of it for those critical weeks, let's examine what the worst-case scenarios actually look like. Not the Hollywood versions, not the simplified narratives of destruction that make for easy storytelling, but the genuinely troubling possibilities that emerge when you combine what we've observed with what we know about the universe, about intelligence, about the vast timescales over which cosmic events unfold. Because the worst case for 3i Atlas isn't that it destroys us. The worst case is that it changes everything we thought we understood, and we're not ready for that change. We've seen interstellar visitors before. This is not humanity's first encounter with objects originating beyond our solar system. In 2017, Oumuamua captured global attention with its peculiar elongated shape and unexpected acceleration as it departed our vicinity. In 2019, 2I/Borisov arrived as an apparently typical comet, complete with visible coma and tail, behaving exactly as cometary science predicted it should. So what makes 3i Atlas different? Why does this particular visitor warrant deeper scrutiny and more unsettling questions? The answer lies in the details that emerge when you move past the simplified narratives and examine what our instruments have actually revealed. 3i Atlas isn't just different from solar system comets. It's different from the previous interstellar visitors in ways that don't quite fit comfortable patterns. Start with velocity. When astronomers calculate the trajectory of 3i Atlas relative to the local standard of rest, the average motion of stars in our galactic neighborhood, they arrive at a figure exceeding 130,000 miles per hour. That's not its speed relative to Earth or even relative to the Sun. That's its velocity through the general stellar environment from which it emerged. To put that in perspective, Oumuamua was moving at approximately 58,000 miles per hour relative to the Sun when it entered the solar system. 2I/Borisov Borisov, clocked in at around 67,000 miles per hour. 3I Atlas is moving substantially faster than both previous visitors, fast enough to complete its entire passage through the inner solar system in a compressed time frame that limits our observation windows. Speed alone doesn't necessarily indicate anything unusual. Objects can achieve high velocities through gravitational assists from stellar encounters or by originating from different regions of the galaxy, where typical stellar motions differ from our local neighborhood. But velocity becomes more interesting when combined with other factors. The trajectory tells a peculiar story. 3I Atlas approaches the solar system on a path that's nearly perpendicular to the ecliptic plane, that flat disk where most planets orbit. Specifically, its orbital inclination measures approximately 175 degrees, meaning it's essentially moving retrograde backwards compared to the general rotation of the solar system. Such inclinations aren't impossible for interstellar objects, given that they come from random directions in the galaxy, but this particular angle brings it remarkably close to the ecliptic plane during perihelion. Think about the geometry for a moment. The galaxy contains trillions of possible trajectories. 3I Atlas could have approached from any direction, at any angle, passing through our solar system at countless different distances from the Sun. Instead, its path threads through in a way that brings it relatively close to the ecliptic, maximizing its proximity to the major planets during its passage. Mars, Earth, Jupiter, all lie roughly in its vicinity during different phases of its trajectory. Statistically, probably not. The solar system occupies a tiny volume of space, and any object passing through it has some chance of approaching various planets. But it's the kind of detail that makes you pause, that plants a seed of curiosity about whether randomness alone explains the geometry we're observing. Then there's the chemical composition, and this is where 3I Atlas truly distinguishes itself. When the James Webb Space Telescope turned its infrared instruments toward this visitor, analyzing the spectroscopic signatures of gases sublimating from its surface as solar heating increased, the results were unexpected. Most comets, both from our solar system and the one previous interstellar comet we've studied in detail, 2I/Borisov, are dominated by water ice. That makes perfect sense. Given formation models, water is abundant in star-forming regions. It condenses readily in the cold environments where comets form. It's the primary volatile component in most cometary bodies. 3I Atlas is different. The ratio of carbon dioxide to water in its outgassing is approximately 8:1. For every molecule of water vapor escaping its surface, 8 molecules of CO2 are released. That's not just unusual. That's almost unprecedented among the comets we've studied in detail. Now, before we venture into speculative territory, let's acknowledge the natural explanations. Cothel-dominated comets can form under specific conditions. If 3I Atlas originated in a region with unusual chemistry, perhaps around a star with different elemental abundances, or if it formed in a particularly cold environment where Cothell's ice could dominate over water ice, the composition makes sense. Some solar system comets show elevated CO5 ratios, though rarely to this extreme. Surface processing offers another explanation. If 3I Atlas has been wandering interstellar space for millions or billions of years, cosmic radiation could have altered its surface chemistry. Water ice might have been preferentially removed or converted to other molecules, leaving a CO2-enriched layer that now faces the Sun as it heats up. These are perfectly valid scientific hypotheses. They don't require anything exotic or unnatural. The universe is vast and chemically diverse. Objects formed under alien conditions will have alien compositions. That's expected, but here's what makes the chemical signature genuinely intriguing. SO5's sublimation requires less heat than water ice. An object dominated by carbon dioxide will begin outgassing at greater distances from the Sun compared to a water ice comet. That means 3I Atlas has been active, shedding material and potentially altering its mass distribution for a longer portion of its inbound journey than a typical comet would. Why does that matter? Because outgassing isn't just visual, it creates thrust. Every molecule that escapes the surface carries momentum, and by Newton's third law, that momentum imparts a tiny push to the comet itself. Over time, these non-gravitational forces can measurably alter an object's trajectory. Astronomers factor non-gravitational acceleration into their orbital calculations. It's standard procedure, well understood, routinely corrected for when tracking comets. 3I Atlas is behaving as expected in this regard. Its trajectory evolution matches predictions based on observed outgassing. Yet the fact remains, an object with unusual chemistry that produces unusual outgassing patterns at unusual distances could, in principle, use those outgassing patterns to make subtle course corrections that would appear entirely natural. If you wanted to navigate while maintaining the appearance of a comet, CO dominance would give you more control over non-gravitational forces than water ice alone. I want to be absolutely clear here. There is no evidence that 3I Atlas is doing anything of the sort. Every observation supports natural behavior, but the chemical composition creates possibilities that wouldn't exist for a more typical comet. And worst-case analysis requires examining possibilities, not just probabilities. The origin of 3I Atlas adds another layer of mystery. Astronomers have attempted to trace its trajectory backward through the galaxy, accounting for stellar gravitational influences and orbital mechanics, trying to identify which star system might have ejected it millions or billions of years ago. The results are frustratingly ambiguous. The most likely scenarios place its origin somewhere in the thick disk of the galaxy, a region populated by older stars with higher metallicities and complex chemical enrichment histories. But pinpointing a specific home system remains elusive. The uncertainties compound as you trace the trajectory backward through time, through multiple stellar encounters that could have perturbed its path, through regions where our knowledge of stellar positions becomes increasingly uncertain. What we can say is this 3I Atlas has been traveling for a very long time. The distances involved, even at 130,000 miles per hour, require millions of years to traverse. This object is ancient. It has witnessed stellar cycles we can barely comprehend. It has survived radiation exposure, micrometeorite impacts, and the gradual chemical evolution that occurs over vast timescales, and it's still coherent. Still solid enough to generate measurable outgassing. Still intact enough to maintain a trajectory that brings it through our solar system with apparent precision, or more fragmented, or at least showed signs of significant deterioration. 2I/Borisov displayed typical cometary behavior with normal disintegration rates. 3I Atlas, for all its unusual chemistry, remains remarkably intact for an object that's been wandering the galaxy for geological ages. Again, natural explanations exist. Perhaps its composition makes it more durable. Perhaps it formed as a particularly dense, well-bound object. Perhaps we're simply seeing it at a favorable point in its evolution before major fragmentation occurs. Or perhaps durability was a design requirement. The size estimates add final details to this portrait. Based on brightness measurements and assumed albedo values, astronomers calculate that 3I Atlas measures somewhere between 1 and 3 kilometers in diameter. That's substantial. Large enough to contain significant mass. Large enough to maintain structural integrity over vast timescales. Large enough to potentially harbour, large enough to harbour whatever imagination suggests it could harbour. Comparing all three interstellar visitors we've now observed, Oumuamua remains the enigma, the weird one with its elongated shape and unexplained acceleration. 2I/Borisov fits comfortably into our understanding of comets, a reassuring visitor that behaved exactly as expected. 3I Atlas occupies the unsettling middle ground, mostly natural, mostly explainable, but with just enough unusual characteristics to prevent comfortable categorization. It's fast but not impossibly so. It's chemically unusual but not inexplicably so. Its trajectory is convenient but not suspiciously so. Its durability is notable but not definitively artificial. Everything about 3I Atlas can be explained naturally. But everything about 3i Atlas also fits the profile of something designed to look natural. And that ambiguity, that fundamental inability to distinguish between those scenarios with our current capabilities, defines the central problem we face as October 29th, 2025 approaches. Because the worst case isn't certainty of artificiality. The worst case is permanent ambiguity, the knowledge that we might have encountered something profound and lacked the tools or wisdom to recognize it before it slipped away forever. October 29th, 2025. The date approaches with astronomical certainty. On that day, 3i Atlas will reach perihelion, passing closest to the Sun at a distance of 1.36 astronomical units. For reference, Earth orbits at 1 astronomical unit by definition, so this interstellar visitor will pass slightly beyond our orbital distance, threading through the gap between Earth and Mars. The geometry of that moment has been calculated with extraordinary precision. The gravitational equations that govern celestial mechanics don't lie, don't fudge numbers, don't allow for uncertainty. We know exactly where 3i Atlas will be on October 29th. We know its velocity at that instant, the solar radiation it will experience, the heating that will drive increased outgassing from its surface. What we don't know is what we'll observe, because during those critical weeks surrounding perihelion, we won't be watching. Solar conjunction occurs on October 21st, 2025. On that date, from Earth's perspective, 3i Atlas will pass within a few degrees of the Sun in our sky. For astronomers, this represents an absolute observational barrier. You cannot point powerful telescopes at objects positioned too close to the Sun without risking catastrophic damage to sensitive instruments. The solar glare overwhelms faint targets. The thermal stress threatens equipment worth millions or billions of dollars. Professional observatories shut down observations of such objects weeks before they reach dangerous proximity. Conservative safety protocols, developed through decades of experience and occasional expensive mistakes, mandate this caution. No single observation is worth destroying an instrument that took years to build and deploy, so we lose sight of 3i Atlas. Not for hours or days, but for approximately 6 weeks. From mid-October through early December 2025, Earth-based observation becomes impossible. The Hubble Space Telescope cannot track it. The James Webb Space Telescope cannot analyze it. Ground-based observatories cannot photograph it. Our most sophisticated surveillance network goes blind at precisely the moment when 3i Atlas undergoes its most dramatic transformation, because perihelion changes everything for a comet. As an icy body approaches the Sun, solar radiation intensifies exponentially. Surface temperatures that were comfortably below freezing suddenly spike. Volatile materials that have been stable for millions or billions of years begin sublimating rapidly. The increased outgassing creates visible coma and tail structures, sometimes triggers surface collapses or fragmentation, always alters the object's appearance and behavior in measurable ways. For a typical comet, perihelion is a spectacular show. Brightness increases dramatically, tail structures extend for millions of miles. Detailed observations during this phase reveal information about internal composition, structural integrity, thermal properties, all sorts of valuable scientific data, and we'll miss it. We'll miss the entire perihelion passage of an interstellar visitor, an object that has traveled for millions of years from a completely alien stellar environment. During the one period when its true nature might reveal itself most clearly, the timing is particularly unfortunate because of what happens after perihelion. Once a comet rounds the Sun and begins its outbound journey, it starts cooling, outgassing decreases, brightness fades. The dramatic display that characterized the approach gradually subsides. By the time 3i Atlas emerges from behind the Sun in early December, it will already be transitioning back toward quiescence. Now, let's be clear about the scientific implications of this observational gap. Astronomers don't expect 3i Atlas to do anything unusual during perihelion. The predictions are straightforward: increased brightness following a smooth curve, enhanced outgassing consistent with CO-FID sublimation at the calculated solar distances, possible minor trajectory adjustments due to non-gravitational forces, all perfectly normal cometary behavior. Those predictions are almost certainly correct. Comets are predictable. We understand their physics. The math works. October 29th will likely come and go, exactly as the models forecast, with 3I Atlas behaving as a well-mannered interstellar comet should. But imagine, for a moment, the worst-case alternative. Imagine that 3I Atlas isn't entirely natural. Imagine that it contains elements or capabilities we haven't detected, designed to activate during perihelion, when solar radiation provides maximum energy input, and when Earth's observation network is guaranteed to be blind. What could happen during those 6 weeks that we'd never detect? Course corrections beyond those explainable by outgassing. Deployment of secondary objects too small to spot against the solar glare. Transmission of signals toward destinations we're not monitoring. Fundamental changes in surface appearance or composition that would be attributed to normal perihelion processing when we finally observe the object again. The beauty of solar conjunction from a certain perspective is that it provides perfect cover. Anything that happened during that window could be retroactively explained as normal perihelion behavior. We have no before and after comparison at high resolution. No continuous monitoring to catch anomalies. No way to definitively prove that the object that emerges in December is identical in all meaningful ways to the object that disappeared in October. Our only witnesses during perihelion will be Mars orbiters. NASA's MOVAN spacecraft and ESA's Mars Express maintain positions that offer different vantage points than Earth. From Mars orbit, with 3I Atlas approaching perihelion on the opposite side of the Sun, observations remain theoretically possible, but Mars orbiters weren't designed for this purpose. Their instruments focus on Martian atmosphere and surface. Their communication bandwidth prioritizes Mars mission data. Their observation windows are limited by orbital geometry and power constraints. Whatever data they collect will be fragmentary at best, unable to provide the continuous high-resolution monitoring that Earth-based facilities could achieve under better geometric conditions. So we wait. We track 3I Atlas through September and into early October, collecting as much data as possible before it slides behind the solar glare. We run our final analyses. We make our predictions. And then we let it go, trusting that perihelion will be uneventful. The early December will bring renewed observation of an object behaving exactly as expected. The December 19th, 2025 close approach offers some consolation. On that date, 3I Atlas will pass within 1.8 astronomical units of Earth, close enough for decent observation with major telescopes, far enough to avoid any conceivable physical interaction. If anything unusual occurred during perihelion, this represents our first opportunity to detect the evidence. But by then, the object will be cooling, fading, already accelerating outward. Any perihelion-specific phenomena will have ceased. Any temporary changes will have reverted. We'll be studying the aftermath, trying to reconstruct what happened from the clues left behind. Never quite certain whether our interpretations capture the full story. And then comes the Jupiter encounter. On March 16, 2026, 3I Atlas will pass within 0.36 astronomical units of Jupiter, closer than the Galilean moons, threading through the space where Jupiter's gravitational influence dominates. For comparison, that's about 33 million miles. Close enough that Jupiter's gravity will measurably alter the comet's trajectory, imparting a gravitational assist that will further increase its outbound velocity. This Jupiter flyby represents the last major event in 3I Atlas's passage through our solar system. The last opportunity for proximity observations. The last chance to detect anything unusual before the object recedes beyond the sensitivity limits of our telescopes. By mid-2026, 3I Atlas will be gone. Not destroyed, not captured, simply gone. Accelerating into the outer solar system at velocities we cannot match with any existing spacecraft. The window of opportunity that opened when astronomers first detected this visitor will have closed permanently. Whatever questions we fail to answer, whatever observations we neglected to make, whatever possibilities we didn't investigate thoroughly enough, will remain forever unresolved. That's the nature of interstellar objects. They don't orbit. They don't return for second chances. They arrive, transit, and depart on timescales measured in months, not decades. The entire arc from detection through perihelion to final observation spans barely 2 years. 2 years to study an object that has been traveling for millions of years. 2 years to understand chemistry that developed under completely alien conditions. 2 years to distinguish between natural and artificial, between random cosmic debris and deliberate something, and within those 2 years, we lose visual contact for the 6 most critical weeks, the period when thermal stress peaks and any hidden capabilities would most likely activate. The worst case scenario isn't that something dramatic happens during perihelion. The worst case is that something subtle happens, something we could have detected with continuous observation but will miss entirely because the sun blocks our view, something that changes the nature of 3I Atlas, in ways we'll only recognize in retrospect if we recognize it at all, because by the time we understand what we should have been looking for, the object will be millions of miles away, receding at 130,000 miles per hour, impossible to recall, impossible to study further. And all we'll have left are the questions we failed to answer when the opportunity existed. Let's explore an uncomfortable possibility. Not because it's likely, but because worst-case analysis demands we consider scenarios that challenge our assumptions about what intelligence looks like and how it might operate across interstellar distances. What if 3I Atlas isn't a comet at all, but rather something designed to look exactly like one? The question sounds absurd until you consider the engineering requirements. An advanced civilization attempting interstellar reconnaissance would face profound challenges. Space is vast. Signals attenuate over distance. Physical spacecraft require energy sources that can sustain them for millennia or longer. Detection by primitive civilizations poses risks that sophisticated actors might want to avoid. Now, imagine you're tasked with designing a probe that can traverse interstellar space, enter foreign solar systems, collect data, and depart without drawing attention. What would such a probe look like? It probably wouldn't look like the sleek starships of science fiction. Those designs make sense for crewed vessels or fast interstellar transit, but they're terrible for long-duration reconnaissance. They're obviously artificial. They create sensor signatures that any civilization with basic astronomical capabilities would detect and track. They announce their presence like neon signs against the cosmic darkness. A better design would mimic nature. It would disguise itself as something common, expected, easily dismissed as natural phenomena. And in the galaxy, few objects are as common or as naturally occurring as comets. Billions of comets populate the Oort clouds of stellar systems. They're ejected through gravitational interactions, sent wandering through interstellar space in numbers we can barely estimate. If you wanted to hide a reconnaissance probe in plain sight, disguising it as a comet provides perfect camouflage. It explains its presence, its trajectory, its behavior, all without raising suspicion. But creating a convincing artificial comet presents staggering technical challenges. You'd need to replicate not just visual appearance, but every physical characteristic that astronomers might measure. Start with outgassing. Real comets sublime ices as they approach stars. That outgassing creates characteristic spectral signatures, visible coma structures, and measurable non-gravitational forces. An artificial object would need to replicate all of that. It would require actual volatile materials on its surface, or sophisticated systems that could generate and expel gases in patterns indistinguishable from natural sublimation. The CO-phetal water-water ratio of 3I Atlas, that 8-to-1 dominance we discussed earlier, suddenly takes on different implications in this context. CO-phi is easier to store and regulate than water. It sublimes at lower temperatures, providing more controllable thrust. If you were engineering an artificial comet's propulsion system, you might deliberately choose CO-phis, as your primary volatile specifically because it offers better maneuverability while still appearing natural. Then there's spectroscopy. When astronomers analyze light reflected from 3I Atlas or emitted by its outgassing envelope, they're measuring precise wavelengths that correspond to specific molecules. An artificial object would need to present authentic chemical signatures across multiple wavelength ranges, from visible light through infrared and into ultraviolet. Any inconsistency, any molecular combination that couldn't exist naturally, would expose the deception, creating materials that pass spectrographic analysis under various conditions, from the frigid temperatures of deep space through the solar heating of perihelion, represents materials science far beyond our current capabilities. But for a civilization capable of interstellar travel, perhaps it's merely difficult rather than impossible. The structural requirements add another layer of complexity. Real comets are loose aggregates of ice and rock, held together by weak gravitational and chemical bonds. They fragment under stress. They rotate irregularly. They show evidence of internal voids and heterogeneous composition. An artificial probe would need to mimic that looseness, that apparent fragility, while actually maintaining structural integrity sufficient to protect sensitive instruments and sustain operations across millions of years. Maybe the solution is embedding the actual probe within a shell of genuine cometary material. Harvest ices and rock from a real comet in your home system, hollow out a cavity, insert your instrumentation, and you've created an object that is authentically cometary in composition while serving artificial purposes. The bulk of the mass is real ice and rock. Only the core carries intelligence. Such a design would pass virtually any chemical or structural test we could perform from a distance. It would outgas naturally because the surrounding material is actually sublimating. It would show authentic spectroscopic signatures because the composition is genuinely icy and rocky. Only internal imaging, impossible without direct contact, would reveal the artificial core. Navigation presents perhaps the most interesting challenge. An interstellar probe must cross vast distances and arrive at specific stellar systems with reasonable accuracy, but obvious propulsion systems create detectable signatures. Fusion drives, ion engines, even solar sails have characteristic features that astronomical observation could potentially identify. Outgassing-based propulsion offers an elegant solution. If you can control when and where your artificial comet releases gases, you can steer it using forces that appear entirely natural. Small course corrections accumulate over millions of years into substantial trajectory changes. And because comets naturally experience non-gravitational acceleration from outgassing, such maneuvers would seem completely expected. The CO dominance of 3I Atlas becomes relevant again here. That unusual chemistry gives the object non-gravitational forces throughout a larger portion of its solar system passage, compared to water-ice comets, more opportunities for subtle steering, more flexibility in final approach trajectories. Now, let's be absolutely clear about something crucial. There is zero evidence that 3I Atlas employs any such system. Its outgassing patterns match natural behavior. Its trajectory evolution fits standard cometary models. Nothing astronomers have observed suggests artificial manipulation. But here's the uncomfortable reality. We wouldn't necessarily detect artificial control even if it existed. Our models of cometary outgassing include uncertainties. We account for unpredictable jets, asymmetric sublimation, rotating nuclei that create complex force vectors. An intelligent system operating within those natural variations could make course corrections that would be statistically indistinguishable from random cometary behavior. Communication raises additional questions. If 3I Atlas were an artificial probe, would it be transmitting data? To where? At what frequencies? Using what protocols? Any civilization sophisticated enough to build interstellar reconnaissance probes would presumably use communication systems optimized for efficiency across cosmic distances. Those systems might not resemble anything in our electromagnetic spectrum. They might use tight beam transmissions aimed at specific stellar coordinates, essentially invisible. unless you're positioned directly in the beam path. They might employ quantum entanglement or other physics we've theorized but not yet harnessed. Or perhaps the probe doesn't transmit at all. Perhaps it's designed to collect data and physically return that data to its origin system. A journey requiring millions of additional years, but avoiding all transmission risks. In such a scenario, we'd never detect any communications because none are being sent. The energy requirements for sustaining operations across millions of years initially seem prohibitive, but consider radioactive decay. A probe powered by radioactive isotopes with appropriate half-lives could maintain basic functionality for geological timescales. Our own Voyager probes, launched in 1977, continue operating decades later using plutonium-238 radioisotope thermoelectric generators. With more efficient power systems and longer-lived isotopes, million-year operational lifetimes become conceivable. Alternatively, a probe might spend most of its journey dormant, powered down to minimal maintenance levels, activating only when solar radiation provides sufficient energy input. Such a design would become active precisely during perihelion, when increased solar flux enables expanded operations. The October 29th perihelion date suddenly takes on additional significance in this context. If an artificial probe were designed to maximize solar power collection while minimizing detection risk from any potential civilizations in the target system, it might specifically plan to activate during perihelion when it's closest to the star and when geometric conditions make observation from nearby planets most difficult, and solar conjunction on October 21st, just 8 days before perihelion, provides that exact observational shield. Again, this is speculation, but it's speculation grounded in rational engineering considerations. If you were designing interstellar reconnaissance systems, these are the kinds of design requirements you'd face, and the solutions you might develop. The surveillance hypothesis raises profound questions about how many such objects might already have passed through our solar system unnoticed. Before 2017, we had never confirmed an interstellar object. Amorma was the first only because we finally had survey systems sensitive enough to detect such visitors. Now within 8 years we've confirmed 3 interstellar objects. How many passed through the inner solar system before our detection capabilities reached current levels? How many are passing through right now, at angles or distances that place them beyond our survey coverage? The Vera Rubin Observatory, scheduled to begin operations soon, will revolutionize our ability to detect such objects. Its wide-field camera and rapid survey capabilities should identify dozens of interstellar visitors per year. Within a decade, we'll have a robust statistical sample, and that's when the surveillance hypothesis becomes testable, at least partially. If interstellar objects arrive at random orientations and velocities, distributed according to galactic stellar kinematics, we'd expect certain statistical patterns. But if a fraction of these objects show subtle preferences, slight correlations that hint at targeting stellar systems with particular characteristics, the patterns might reveal artificial selection. It's worth noting that such surveillance wouldn't necessarily imply hostility. Scientific curiosity exists independent of aggressive intent. A galaxy-spanning civilization might conduct reconnaissance for the same reasons we study distant exoplanets. Pure knowledge-seeking, categorizing stellar systems, monitoring the development of potential new intelligences. The dark forest hypothesis, popularized by science fiction but rooted in game theory, suggests that civilizations avoid revealing themselves because any contact carries existential risk. In such a framework, covert surveillance makes perfect sense. You'd want to know what's out there without announcing your own presence. Whether 3i Atlas fits that framework remains unknowable with current data. What we can say is that if advanced intelligence decided to surveil our solar system, an object behaving exactly like 3i Atlas would represent an extraordinarily effective approach. Natural enough to avoid triggering alarms, unusual enough to potentially carry significant capabilities, fast enough to complete observations and depart before detailed investigation becomes possible, The worst case under the surveillance hypothesis isn't invasion or destruction. It's simpler and stranger than that. The worst case is that we're being studied, catalogued, assessed by intelligences we cannot detect using methods we cannot recognize, and that this reconnaissance has been ongoing for far longer than we imagine. Because if one comet-shaped probe can pass through convincingly, there's no reason to assume it would be alone. Let's conduct a thought experiment. Suppose that on December 5th, 2025, when 3M Atlas emerges from behind the Sun and becomes observable again, something has changed. The object's brightness doesn't match predictions. Its spectrum shows anomalous features. Its trajectory has deviated in ways that cannot be explained by outgassing alone. Suppose that within days of this revelation, multiple research teams confirm the anomalies. The European Space Agency releases a statement acknowledging unexpected observations. NASA schedules emergency press conferences. The astronomical community erupts into furious debate as decades of assumptions about interstellar objects suddenly collapse. And suppose that within weeks, the consensus crystallizes around an uncomfortable conclusion. 3I Atlas exhibits characteristics inconsistent with natural origin. The evidence doesn't prove artificial origin beyond all doubt, but it makes the natural explanation increasingly untenable. What happens next? The honest answer is that nobody knows. We've never faced this situation. We've never confirmed artificial objects in our solar system beyond our own spacecraft. We've never encountered intelligence that didn't originate on Earth. Our protocols, our institutions, our political frameworks, none of them are actually prepared for this scenario, despite decades of speculation and science fiction. Start with the immediate jurisdictional questions. Who has authority to speak for humanity? The United Nations Office for Outer Space Affairs exists and maintains responsibility for coordinating international space policy, but its mandate focuses on activities conducted by humans in space, not responses to alien artifacts discovered within our solar system. DETI, the Search for Extraterrestrial Intelligence Community, has developed contact protocols over decades. These protocols outline suggested procedures if we receive artificial radio signals from space. They emphasize scientific verification, international consultation, and measured public disclosure. But SETI protocols assume passive detection of distant signals, not active physical objects already present in our immediate cosmic neighborhood. NASA would presumably take a leading role given its capabilities and mandate, but NASA is a civilian space agency of the United States government. Other nations with substantial space programs, China, Russia, India, Europe, Japan, would rightfully demand participation in any response framework, and the speed at which 3M Atlas moves through the solar system would compress the timeline for international coordination to weeks or months at most. The European Space Agency would certainly claim joint authority. Roscosmos, despite political tensions, possesses unique capabilities. The Chinese National Space Administration has rapidly developed sophisticated spaceflight expertise. Any meaningful response would require international collaboration on an unprecedented scale, negotiated under intense time pressure with absolutely no precedent to guide the process. Then there's the military dimension. Defense establishments worldwide would immediately classify 3I Atlas as a potential security concern. Intelligence agencies would demand access to all data. Strategic planners would begin assessing capabilities and intentions, despite having virtually no information on which to base such assessments. The conflict between military secrecy and scientific transparency would become immediate and intense. Scientists require open data sharing to conduct proper analysis. Military and intelligence communities reflexively classify information related to potential threats. These competing imperatives have produced friction in far simpler contexts. With genuine alien technology at stake, the tensions could become paralyzing. Public disclosure presents its own nightmare scenario. Authorities would face impossible choices about timing and content. Announce too early before confirmation is solid, and you risk global panic over what might turn out to be natural phenomena with unusual characteristics. Wait too long, allowing information to leak through unofficial channels, and you've lost control of the narrative while generating justified anger about deliberate concealment. Social media would accelerate and complicate everything. The first astronomer to notice anomalies might tweet observations before official channels could coordinate responses. Amateur astronomers have sophisticated equipment. They follow interstellar objects closely. Any actual anomalies would be independently detected quickly, making coordinated disclosure impossible. Imagine the information chaos that would erupt, competing analyses from different research groups reaching different conclusions. Conspiracy theories launching before official statements could establish factual baselines, political exploitation, as various actors use the situation to advance unrelated agendas. Religious institutions grappling with theological implications while their members demanded guidance. The economic impacts could be substantial even without any direct threat. Market volatility, as uncertainty spooked investors. Defense budgets surging as nations competed to develop response capabilities. Scientific research funding shifting dramatically towards space-related programs. All of this occurring while authorities still tried to determine what they were actually dealing with. Then there's the communication challenge. If 3i Atlas were confirmed as artificial, would we attempt communication? Should we? Who decides? The object would still be receding at over 130,000 miles per hour. Radio signals travel at light speed, meaning messages could reach it, but the geometry becomes increasingly unfavorable as it moves away. Any meaningful exchange would require sustained transmission efforts using major radio telescopes. But what message would we send? Greetings? Questions? Demands? And in what format? Mathematical language seems like the obvious choice, but our understanding of what constitutes universal mathematical communication is remarkably limited when you examine it closely. We assume mathematics is universal, but the specific notations and conceptual frameworks we use are culturally bound. Moreover, transmitting messages toward an object of unknown origin and intent carries risks that some would consider unacceptable. You're announcing your presence, your capabilities, your location. You're providing data about your civilization to an intelligence that has revealed itself only ambiguously. The strategic implications make military planners extremely nervous. The active SETI debate, arguing over whether humanity should deliberately transmit signals into space, has been ongoing for years without resolution. The 3i Atlas scenario would force that debate to a conclusion within weeks, under conditions of maximum pressure and minimum information. Perhaps the object would initiate communication. Perhaps anomalous behavior would include deliberate signaling, radio transmissions, or optical pulses clearly designed to convey information. That would resolve some uncertainties while creating new ones. Who receives the message? In what language? What if different nations receive different messages? The scenario planning becomes increasingly Byzantine the more you examine it. International law has no framework for this. National legal systems offer no guidance. Ethical principles that seem clear in abstract discussion become murky when faced with actual choices under time pressure. And time pressure would be relentless. 3i Atlas won't linger waiting for humanity to sort out its governance problems. By March 16th, 2026, it flies past Jupiter. By mid-2026, it's beyond effective observation. Within a few years, it will be farther from the Sun than Neptune, effectively gone from our immediate concern. If humanity wanted to send a physical mission to intercept 3i Atlas, to examine it directly rather than relying on remote observation, the launch window would be extraordinarily narrow. No existing spacecraft could match its velocity. No mission architecture is prepared. The fastest probe we've ever launched, New Horizons, took 9.5 years to reach Pluto at velocities far slower than 3i Atlas. A crash program to develop and launch an interceptor mission would cost tens of billions of dollars, require international cooperation on an unprecedented scale, and face technical challenges we've never confronted. And it would need to commence within months of confirming artificiality to have any chance of success. The political will to fund such a mission while simultaneously dealing with economic disruption, social anxiety, and institutional chaos seems questionable at best. Yet the scientific and strategic value of direct examination would be incalculable. The tension between what we should do and what we could actually organize in time defines another dimension of the nightmare. Perhaps the worst aspect of the protocol nightmare is that we're having this conversation in 2024, with October 2025 already visible on the horizon, and none of these issues have been seriously addressed at the governmental or international level. The institutions that would need to respond are unprepared. The coordination frameworks don't exist. The public conversations haven't happened. If 3i Atlas does turn out to be something other than natural, we'll be improvising our response in real time, making civilization-level decisions with inadequate information, under intense time pressure, without tested protocols or established authorities, and that improvisation, that chaos of competing interests and uncertain authority, might represent the actual worst case. Not what the object itself does, but how humanity fails to respond coherently, fractures under pressure, makes avoidable mistakes, because we never seriously prepared for the possibility we've been hypothesizing about since the dawn of the space age. The question isn't whether 3i Atlas is artificial. The question is whether we could handle discovering that it is. Let's return to the most tangible, unusual characteristic of 3i Atlas, that 8:1 ratio of carbon dioxide to water in its outgassing composition. The James Webb Space Telescope measured this. It's not speculation. It's data, strange data, that deserves deeper consideration. Every molecule represents a specific arrangement of atoms, a particular solution to the equations of quantum mechanics that govern how particles bond and interact. When we analyze the chemical composition of an object, we're reading a history written in atomic arrangements, a story of formation conditions, thermal processing, chemical evolution across vast timescales. But chemistry can also be communication. Information can be encoded in molecular patterns, in ratios and distributions that carry meaning beyond their immediate physical properties. This is how DNA works, after all. The specific sequence of nucleotide bases encodes biological information using chemical arrangements. So here's an unsettling question. If an advanced intelligence wanted to leave a message that would be detected by any civilization capable of spectroscopic analysis, but that would appear natural to less technologically sophisticated observers, could they encode that message in the chemistry of an artificial comet? The concept isn't as absurd as it initially sounds. Consider what spectroscopy reveals. When we analyze light reflected from or emitted by an object, we're measuring precise wavelength patterns corresponding to specific molecular transitions. Each molecule has a unique spectroscopic signature, a fingerprint created by the quantum energy levels of its electrons. A sufficiently advanced civilization would understand spectroscopy far better than we do. They could design materials with specific spectroscopic properties, creating molecular combinations that produce particular patterns when analyzed. Those patterns could carry information distinct from the natural chemistry they superficially resemble. The CO5 to water ratio is the most obvious unusual feature, but the full spectrum detected by Webb is far more complex. Trace molecules exist in various abundances. Isotopic ratios show subtle variations. The temperature-dependent sublimation creates temporal changes in the observed spectrum as different ices vaporize at different solar distances. All of that complexity is interpreted through natural frameworks. We assume the ratios reflect formation conditions. We attribute isotopic variations to chemical evolution or radiation processing. We model the temperature-dependent changes using cometry physics. But what if some of those features are deliberate? What if the distribution of rare isotopes follows a pattern that encodes information? What if the exact timing of when different molecules begin outgassing carries meaning beyond natural sublimation points? To us, analyzing the data with our current frameworks, it all looks like natural chemistry. But to a civilization searching for artificial patterns, perhaps trained to recognize specific molecular distributions as signatures of intelligence. The same data might reveal an entirely different layer of meaning. This is the challenge of steganography, hiding information within apparently innocent content. In human contexts, we've developed sophisticated techniques for embedding secret messages in digital images, audio files, or text documents. The carrier medium appears normal to casual observation, but specific analysis reveals hidden content. Chemical steganography would operate on the same principle. The comet appears chemically normal, explicable through natural processes, but certain molecular ratios or distributions encode additional information detectable only by those who know what to look for. How would you design such a system? Start with the constraint that the overall chemistry must remain plausibly natural. You can't use molecular combinations that couldn't exist in any natural environment. That would immediately trigger suspicion. Your encoding must work within the parameters of possible cometary chemistry. Isotopic ratios offer an interesting channel. Most elements exist in multiple isotopic forms, variations with different numbers of neutrons. Natural processes create specific isotopic distributions, but the exact ratios can vary based on formation environment and subsequent processing. Small, deliberate adjustments to those ratios could encode information while remaining within the envelope of natural variation. Spectroscopy can detect isotopic differences. The mass changes from additional neutrons create subtle shifts in molecular vibration frequencies, producing measurable spectral changes. Webb's instruments are sensitive enough to detect these variations in principle, though analyzing them requires careful work to separate signal from noise. If 3I Atlas contains deliberately adjusted isotopic ratios encoding information, would we recognize them? Probably not, unless we were specifically searching for such patterns. Our analysis focuses on bulk chemistry and overall composition. Isotopic studies happen, but they're interpreted through natural frameworks. We'd attribute variations to natural processes, unless the patterns were so obvious that natural explanations became untenable. The temporal dimension adds another encoding channel. As 3I Atlas approaches the Sun, different ices sublimate at different temperatures and solar distances. Water ice sublimates at warmer temperatures than CO2. Other volatiles, carbon monoxide, methane, nitrogen, various organics, each have specific sublimation points. The sequence in which these molecules appear in the outgassing spectrum creates a timeline, a changing chemical signature as solar heating intensifies. That timeline could encode information. The exact solar distance at which particular molecules begin outgassing, the relative abundances as functions of heliocentric distance, the way different species correlate or anti-correlate with each other, all of this temporal evolution can be explained naturally. We have thermal models of cometary nuclei. We understand how solar radiation penetrates surface layers, how heat conducts through porous ice, how volatile molecules migrate and eventually escape. But those natural models include uncertainties. They allow for variations based on composition, structure, albedo, rotation, a deliberately engineered temporal sequence designed to fall within natural variations while encoding specific patterns would be extraordinarily difficult to distinguish from random natural behavior. Then there's the question of what message such chemistry might encode. Basic information about the sender, mathematical sequences proving artificial origin, warnings, invitations, instructions, or perhaps the chemistry itself is the message. Perhaps the very fact of unusual but not impossible molecular distributions is meant to trigger curiosity in civilizations sophisticated enough to conduct detailed analysis, not encoding specific content, but serving as an attention flag, a deliberate puzzle saying, "Look closer, there's something here worth investigating further." The CO-theist dominance becomes intriguing from this perspective. It's unusual enough to warrant scientific interest, to generate papers and detailed spectroscopic studies. But it's not so unusual as to be impossible naturally. It sits precisely at the boundary between explainable and mysterious, guaranteed to attract focused attention from any civilization capable of interstellar astronomy. Is that deliberate optimization? Or are we pattern-seeking primates reading intention into random chemical accidents? The question is fundamentally unanswerable. With our current data, we'd need far more detailed compositional analysis, sustained monitoring throughout the entire perihelion passage, direct sampling missions that could return material for laboratory study. Even then, distinguishing deliberate patterns from natural chemistry would require knowing what to look for, and that's assuming the message, if one exists, is meant for civilizations at our developmental level. Perhaps the encoding operates at scales, or using principles we haven't discovered yet. Perhaps our spectroscopy is too crude to detect the relevant patterns. Perhaps we're looking at profound communication and seeing only ice and gas because our conceptual frameworks are inadequate. The philosopher's stone of this scenario is that chemistry is universal. Carbon dioxide is carbon dioxide whether it forms in our solar system or a stellar environment, 100 light-years away. The physical laws governing molecular bonds don't change across the galaxy. Any intelligence that exists must deal with the same periodic table, the same quantum mechanics, the same thermodynamics we've discovered. So if you wanted to leave a message that could be detected across space and time by any technologically sophisticated civilization, encoding it in chemistry offers certain advantages. It's durable, stable for millions of years in the cold of interstellar space. It's detectable from a distance using spectroscopy, which any scientifically advanced civilization will develop. And it's analyzable using universal physical principles, but the same universality that makes chemical encoding attractive also makes it potentially indecipherable. Without a Rosetta Stone, without some reference frame to distinguish deliberate patterns from natural variations, we could be staring at a message and seeing only molecules. The speculation deepens when you consider that 3I Atlas has been traveling for millions of years. If it were an artificial messenger, the civilization that created it could be radically different now than when they launched it. They might have evolved, transcended, gone extinct. The message encoded in an ancient probe might be the only surviving remnant of entire civilizations, and if that message is written in chemistry in the patient language of atoms and molecules, it would remain readable for geological ages, waiting for someone to notice the patterns, to recognize that the randomness isn't quite random, to understand that these particular molecular distributions carry meaning beyond their thermodynamic properties. October 29th, 2025 approaches, and with it the most intense chemistry that 3I Atlas will display. As perihelion heating drives maximum outgassing, as volatile materials long frozen begin sublimating in complex sequences, the complete chemical story of this object will unfold, and we won't be watching, we'll be blind, forced to reconstruct the perihelion chemistry from later observations, from the residue and after effects rather than the main event. If there's a message written in the molecular patterns of 3I Atlas, if the chemistry encodes meaning beyond its apparent naturalness, perihelion is when that message would be most clearly expressed, and we're going to miss it. Trajectories tell stories. When you trace an object's path backward through space and time, accounting for gravitational influences and orbital mechanics, you're reading a history written in celestial coordinates, a narrative of where something has been, and what forces have shaped its journey. 3I Atlas is moving at 130,000 miles per hour through the local stellar neighborhood. That velocity vector points back towards somewhere, some stellar system or interstellar region where this journey began millions of years ago. Astronomers have attempted to trace that trajectory backward, running the equations in reverse, trying to identify the object's origin. The calculations are extraordinarily complex. You must account for every stellar encounter along the way, every gravitational perturbation that might have altered the path. You need accurate positions and velocities for thousands of stars in the relevant volume of space, data that becomes increasingly uncertain the further back you trace. The results are frustratingly ambiguous. Multiple stellar systems emerge as possible candidates for ejecting 3I Atlas. The thick disk of the galaxy, That region of older stars with varied chemical compositions seems likely, but pinpointing a specific home star remains beyond current capabilities. That ambiguity is normal and expected. Tracing interstellar trajectories backward through millions of years of galactic evolution involves compounding uncertainties. Small measurement errors in current position and velocity create enormous uncertainties in ancient history. It's like trying to determine where a particular raindrop originated by measuring where it lands in the ocean. But here's what troubles some astronomers when they examine the trajectory in detail: the approach angle. The specific geometry of how 3I Atlas enters our solar system shows a curious feature. Despite coming from what appears to be a random direction in the galaxy, its path brings it remarkably close to our ecliptic plane during perihelion. The ecliptic is that flat disk where Earth and most other planets orbit. It represents the remnant angular momentum from the solar system's formation, the plane around which most mass in our system concentrates. From an outsider's perspective, the ecliptic is the most obvious and significant feature of our solar system's geometry. 3I Atlas approaches from a steep angle, that 175-degree inclination, indicating a highly tilted path. Yet, at perihelion, at the moment of closest solar approach, it passes relatively near the ecliptic plane. Not directly through it, but close enough that Earth, Mars, and eventually Jupiter lie in reasonably favorable positions for observation. Is that meaningful? Statistically, probably not. The solar system occupies a three-dimensional volume. Any object passing through has some chance of approaching various regions. The fact that 3I Atlas happens to pass near interesting planetary orbits might be pure coincidence, but coincidences accumulate. The high velocity from an unusual direction, the chemical composition, unlike typical comets, the timing of perihelion during observational blind spots, the proximity to major planets. Each individual feature has natural explanations. Together, they create a pattern that makes you pause. Imagine you're designing an interstellar reconnaissance probe. You want to study a stellar system, specifically investigating whether it hosts habitable planets or developing civilizations. How would you approach? You'd want to pass near the habitable zone, that region where liquid water could exist on planetary surfaces. For our solar system, that's roughly the orbital distance of Earth and Mars. You'd want your trajectory to bring you close enough for detailed observation, but not so close that you risk collision or detection. And you'd probably want to cross through the ecliptic plane or pass near it, because that's where planets are most likely to be found. A path that stays far above or below the ecliptic might miss all the interesting objects you're trying to study. So the trajectory of 3I Atlas, approaching from high inclination but threading through the ecliptic region during perihelion, matches what you might design if you were conducting reconnaissance. Again, this proves nothing. It's pattern matching, seeking meaning in geometry that might simply reflect random chance. But the pattern exists, and worst-case analysis requires examining such patterns even when natural explanations remain possible. Recent studies have attempted more sophisticated trajectory analysis, using detailed galactic models and enhanced stellar position data from Gaia, the European Space Agency's star mapping mission. These efforts have narrowed the possible origin candidates somewhat, but haven't achieved definitive identification. Part of the challenge is temporal. The longer 3I Atlas has been traveling, the more stellar encounters could have perturbed its path, the more gravitational interactions complicate the backward calculation. If this object has been wandering for 10 million years, tracing its path with precision becomes nearly impossible. If only a million years, the calculation might be tractable with sufficient data. Age estimation for interstellar objects is indirect and uncertain. You can estimate based on surface weathering, on the density of impact craters, if you had high-resolution imagery, on chemical evolution indicators, if you understood the radiation environment it traversed. But without direct sampling or extremely detailed observations, you're guessing. What we can say with confidence is that 3I Atlas has traveled far, The distances between stars ensure that even at 130,000 miles per hour, interstellar journeys require geological time. This object is old, ancient in human terms, has experienced more stellar cycles than civilizations have risen and fallen on Earth, and throughout all that time, it maintained structural integrity. It remained coherent enough to survive as a discrete object rather than fragmenting into undetectable debris. It preserved its chemical composition well enough that we can analyze it today. It arrived at our solar system on a trajectory that, coincidentally or not, brings it through the most astronomically interesting region. The counter-argument to any trajectory-based suspicion is simple. We're seeing selection bias. We detected 3I Atlas precisely because its trajectory brought it relatively close to Earth. If it had passed through the outer solar system at greater distances, we might have missed it entirely. So of course the interstellar objects we detect will have trajectories that favor detection. That's tautological, but the ecliptic crossing isn't just about detection. It's about geometry that maximizes observational value for someone studying the solar system. It's about a path that samples the habitable zone efficiently. And then there's the timing. October 29th, 2025 isn't arbitrary from an astronomical perspective. It's the point of closest solar approach, the moment when 3I Atlas experiences maximum heating and presumably maximum activity. But it's also, almost coincidentally, a period when Earth-based observation becomes nearly impossible due to solar conjunction. If you were navigating deliberately, if you wanted to maximize energy collection from solar radiation while minimizing observation from any resident civilization, you'd probably target perihelion to occur during solar conjunction from the perspective of major planets. That's exactly what we're seeing, or it's coincidence, or it's selection bias, because we detected this particular object partially due to favorable earlier geometry, or it's the anthropic principle. We exist in a universe where this trajectory happens, so of course we observe it. The pattern recognition becomes almost maddening. Every unusual feature can be explained naturally. Every suspicious coincidence has reasonable alternatives, but the accumulation of individually explainable oddities creates an overall impression that something deserves deeper scrutiny. The trajectory of 3I Atlas has been calculated. The equations are solved. We know where it's going, where it's been in broad terms, how it will exit the solar system after its Jupiter flyby. The orbital mechanics are settled science. What remains uncertain is whether that trajectory was purely shaped by natural gravitational forces acting on a random object ejected from some distant stellar system millions of years ago, or whether intelligence influenced this path, making corrections too subtle to detect. Navigating toward this stellar system for purposes we can only guess, December 2025 brings renewed observation. March 2026 offers the Jupiter flyby. Throughout those months, precise astrometric measurements will track 3I Atlas's position against background stars. If any trajectory deviations appear that cannot be explained by outgassing forces and gravitational interactions, if the path shows evidence of active control, but even then, even if anomalous acceleration were detected, would we interpret it correctly? Would we recognize artificial navigation, or would we simply expand our models of cometary non-gravitational forces to accommodate the new data, preserving natural explanations, because artificial ones seem too extraordinary to accept without overwhelming evidence? The trajectory troubles astronomers not because it's impossible naturally, but because it's convenient artificially. And that convenience, that alignment between what we observe and what we might design, whispers possibilities we're not quite ready to seriously entertain. But October 29 approaches. Perihelion arrives. The trajectory carries 3I Atlas through the moment of closest solar approach on a path that has taken millions of years to traverse. And whether that path was random wandering or deliberate navigation remains, for now, a question written in the mathematics of celestial mechanics, awaiting observations we hope will provide answers, fearing they might only deepen the mystery. Let's examine a scenario that's existentially uncomfortable in ways that have nothing to do with immediate threat. What if 3i Atlas is artificial, but its creators are gone? The Great Filter concept originates from attempts to resolve the Fermi paradox, that troubling discrepancy between the apparent high probability of extraterrestrial civilizations and the complete absence of evidence for their existence. Something, the reasoning goes, filters out civilizations. Either there's a barrier in the past that makes technological intelligence incredibly rare, or there's a barrier in the future that prevents civilizations from surviving long enough to become observable across interstellar distances. If the filter lies ahead of us, if something prevents most civilizations from achieving long-term stability and cosmic expansion, then the galaxy might be full of ruins, failed experiments in intelligence, extinct civilizations that briefly flourished before encountering whatever catastrophe the filter represents. Now imagine that 3i Atlas is a probe from such a civilization, launched millions of years ago during a period of technological optimism and interstellar ambition, sent out to explore, to gather data, to perhaps identify other emerging intelligences that might become partners or rivals, but the civilization that built it no longer exists. Maybe they destroyed themselves through nuclear war or environmental collapse. Maybe artificial intelligence turned against them. Maybe resource depletion or pandemic triggered civilizational collapse. Maybe they encountered something unexpected that we haven't yet imagined. Whatever the cause, they're gone, but their probe continues, following programming established eons ago, visiting stellar system after stellar system on a journey that might continue for billions of years, long after every trace of its creators has eroded to cosmic dust. This scenario is troubling, not because it's threatening, but because of what it implies. If we confirm that 3i Atlas is artificial, that alone would be the most significant discovery in human history. Proof that we're not alone in the universe. Proof that intelligence can arise elsewhere. But if further investigation suggests the probe is ancient, a relic from a civilization that no longer exists, then we've discovered something far more unsettling. We've found evidence of the Great Filter in action. We've confirmed that intelligence can fail, that civilizations can develop technology sufficient for interstellar engineering and still go extinct. And if it happened to them, with their presumably advanced capabilities, why would we assume it couldn't happen to us? The temporal scales involved make this scenario particularly haunting. 3i Atlas has been traveling for at least millions of years, possibly longer. During Earth's timeline, millions of years ago takes us back before human evolution, back to when our ancestors were primitive primates, back to when intelligence as we understand it didn't exist on this planet. Some ancient civilization, looking out at the galaxy, made the decision to explore. They invested resources into building probes that could survive interstellar journeys. They developed navigation systems, power sources, instruments, all designed to function across timescales that dwarf recorded human history. And then they disappeared. Perhaps gradually, their civilization declining over centuries or millennia. Perhaps suddenly, in a catastrophic cascade, they didn't predict or couldn't prevent. But by the time 3i Atlas arrives at our solar system, billions of miles and millions of years from its origin, there's no home to return to, no masters to receive its data, no civilization to appreciate what it has observed. Just an automated explorer, faithfully executing programming established by beings who have been extinct for geological ages, continuing a mission that has lost all purpose except that which the probe itself maintains through its design. The philosophical implications are staggering. Here would be an artifact of intelligence, proof of technological sophistication, evidence of curiosity and ambition, and the desire to understand the cosmos, but also evidence that none of those qualities guarantee survival. The same intelligence that can build interstellar probes can apparently fail to navigate whatever challenges the Great Filter represents. What destroyed them? Was it something universal, a challenge that every technological civilization inevitably faces? Or was it specific to their circumstances, their planet, their biology, their choices? If universal, Then 3i Atlas becomes a warning, a message from the past not encoding information but embodying it. We were here, we achieved this, and we're gone. The comet-shaped messenger serves as a tombstone, the only remaining marker of a vanished civilization. If specific to their circumstances, then perhaps we can avoid their fate, perhaps by studying this artifact, by understanding the technology level it represents and the age at which its civilization vanished. We can identify danger periods in our own development and navigate them more successfully. But how would we extract such information from a comet that might or might not be artificial? What tests could distinguish between a recent probe from an extant civilization and an ancient probe from an extinct one? Age estimation would be crucial. If we could determine when 3i Atlas was constructed, we'd know whether we're dealing with contemporary technology or ancient artifacts. But dating an object in space, without direct sampling, without the geological context that makes radioactive dating possible on Earth, seems nearly impossible. We might look for degradation patterns. Artificial objects exposed to cosmic radiation for millions of years should show specific damage signatures, isotopic changes from particle bombardment, erosion patterns from micrometeorite impacts. But if the probe is shielded within genuinely cometary material, that analysis becomes far more difficult. We might search for technology aging. If 3i Atlas contains artificial components, they might use materials or engineering approaches that seem obsolete compared to what we'd expect from a contemporary advanced civilization. But how do we recognize obsolete alien technology? We have no reference frame for what their engineering looked like at different developmental stages. The power source might offer clues. Radioactive isotopes decay on known timescales. If the probe uses radioisotope generators, the decay products might indicate age, but only if we could sample them directly, and only if we understood which isotopes they chose and why. Perhaps the most unsettling aspect of the extinct civilization scenario is that it makes first contact a one-way experience. We detect evidence of intelligence, possibly even receive messages or data embedded in the probe, but there's no opportunity for dialogue. No chance to ask questions, no way to learn about their culture, their history, their mistakes, except through reverse engineering and speculation. It's like archaeology on a cosmic scale, except instead of excavating ruins that have been sitting on one planet's surface, you're trying to understand an entire civilization from a single artifact that has been traveling through the void for millions of years. What could 3i Atlas tell us about its creators if we had the opportunity for detailed study? The materials science would reveal their access to various elements, their capabilities in fabrication and assembly. The power systems would indicate their energy technology level. The instrumentation would show what kinds of data they valued, what they were trying to learn about the universe. The navigation systems, if we could access them, might contain the most valuable information, star charts showing their location, trajectory plans indicating which systems they were targeting, perhaps even databases of previous observations from other stellar systems the probe has visited. Imagine recovering that data. Imagine accessing millions of years of observations from dozens or hundreds of solar systems across a vast volume of space. The scientific value would be incalculable. The strategic implications of knowing where an advanced civilization arose, even an extinct one, would be profound. But all of that assumes we could reach the probe, match its velocity, conduct detailed examination. Given that 3i Atlas is moving at 130,000 miles per hour and will exit the solar system within a few years, such a mission seems beyond current capabilities unless we commit to it immediately with unprecedented resources and international cooperation. So we're left with remote observation, spectroscopy, trajectory analysis, trying to extract maximum information from limited data before the object disappears. If it is an ancient artifact, we might recognize some of its artificiality, but miss most of what it could teach us. Forever wondering what knowledge we let slip away, the Great Filter scenario forces us to confront uncomfortable questions about our own trajectory. We're currently at what might be a critical juncture in human civilization. We have technology sufficient to destroy ourselves through nuclear war, environmental damage, or potentially through artificial intelligence development. We're facing challenges, climate change, resource depletion, biodiversity loss, that could trigger collapse if unaddressed. Are we approaching our own filter? Is there some threshold ahead where most civilizations fail, where the complexity of maintaining technological society exceeds our capability to manage it sustainably? If 3i Atlas represents evidence that another civilization passed through early filter stages, developed interstellar capabilities, and then still went extinct, that suggests the filter might lie further ahead than we hoped. It suggests that even civilizations more advanced than ours, with presumably greater wisdom and technological resources, couldn't navigate whatever challenges ultimately destroyed them. That's the existential dread embedded in this scenario. Not fear of alien invasion, not concern about immediate threats, but rather the dawning recognition that intelligence might be fundamentally unstable across long timescales, that the same curiosity and innovation that drives exploration and scientific discovery also generates risks we may be unable to manage indefinitely. Of course, this entire line of reasoning assumes that if 3i Atlas is artificial, its creators are extinct. That's not necessarily true. Maybe they're thriving, expanding, building Dyson spheres and colonizing the galaxy, and this is merely one probe among millions conducting long-duration surveys. Maybe they're deliberately silent, avoiding contact for reasons we don't understand. But if they're extinct, if we're looking at a monument to vanished intelligence, then 3i Atlas transitions from fascinating scientific anomaly to mirror reflecting our own potential future. October 29th, 2025, perihelion passage could mark the moment when humanity first confronts concrete evidence of its own mortality on civilizational timescales. Not through abstract philosophical reasoning, but through the discovery of a physical artifact proving that intelligence isn't enough, that technological capability doesn't guarantee survival, that somewhere in the vast darkness between stars another civilization tried and failed, and their failure, encoded in the trajectory of a comet that might not be a comet, becomes our warning. A message written not in radio signals or mathematical sequences, but in the simple fact of continued existence without the presence of creators. The worst case isn't that we're alone in the universe. The worst case is discovering we're not alone, but that intelligence tends toward extinction, and we're looking at our own probable fate accelerating toward us at 130,000 miles per hour, in the form of an ancient probe whose civilization couldn't answer the questions we're just beginning to ask. October 29th comes and goes. Perihelion passes, behind the solar glare, invisible to our instruments. 3i Atlas completes its closest approach to the Sun and begins the long acceleration outward. We mark the date, knowing something happened, some transformation occurred as intense solar radiation battered the object. But we didn't witness it. Then comes the waiting. Days stretch into weeks as 3i Atlas continues its trajectory away from perihelion, but still too close to the Sun for safe observation. The geometry slowly improves. The angular separation between comet and star gradually increases. Early December 2025 brings renewed visibility. Major observatories begin scheduling observation time. Amateur astronomers point their telescopes toward the coordinates where 3i Atlas should appear. The first images start arriving, processed, analyzed, compared against pre-perihelion data. This is the moment of truth. What has changed? For a typical comet, perihelion transforms appearance dramatically. Pre-approach, they're often faint, showing minimal activity. Post-perihelion, they're brighter, more active, with extensive coma and tail structures visible. The intense solar heating drives massive outgassing, stripping away surface layers, sometimes causing fragmentation, always altering the object's properties in measurable ways. 3i Atlas should follow similar patterns if it's entirely natural. The predictions are clear. Specific brightness increase based on size and composition, enhanced CO thig, outgassing producing measurable coma, possible dust emission creating visible tail, gradual decline in activity as it recedes and cools. Any deviations from those predictions become immediately significant. If brightness doesn't match expectations, if the spectrum shows unexpected changes, if the morphology differs from models, astronomers will have questions demanding answers, and depending on what those deviations are, if they exist, we might finally have the evidence to distinguish between natural and artificial. Imagine 3I Atlas emerges from perihelion darker than expected, significantly less active, as if something prevented the anticipated outgassing surge. Solar heating is unambiguous. At 1.36 AU, the radiation flux is calculable. If the object doesn't respond as predicted, either our composition estimates were wrong, or something about its structure isn't what we assumed, or imagine the opposite, far more active than expected. Brightness increases beyond what sublimation alone could explain. Additional spectral features appear that weren't present pre-perihelion. Gas production rates inconsistent with the estimated size and composition, either deviation triggers intensive investigation. Natural explanations would be explored first. Maybe we misjudged the size. Maybe rotation exposes fresh ice layers. Maybe internal structure is more porous than anticipated, allowing better heat penetration and more extensive sublimation. But if natural explanations seem inadequate, if the changes appear too specific or too controlled, then the artificial hypothesis moves from fringe speculation to serious consideration. The aspect ratio and shape become measurable with post-perihelion observations. If 3I Atlas emerges with a different light curve, indicating altered rotation or changed shape that demands explanation, comets can fragment during perihelion, torn apart by thermal stress or tidal forces, but specific shape changes, elongation or compression beyond what fragmentation should cause, might indicate internal mechanisms we didn't predict. Then there's trajectory. The real test comes from precise astrometry, measuring 3I Atlas's position against background stars over weeks and months following perihelion. Those measurements allow calculation of any trajectory changes beyond expected gravitational effects and outgassing acceleration. If additional forces appear, if the post-perihelion trajectory shows deviations inconsistent with models, astronomers face difficult questions. Was internal structure more irregular than assumed, creating asymmetric outgassing jets? Did fragmentation occur during perihelion, altering mass distribution? Or did something change deliberately, taking advantage of perihelion's high activity to mask intentional maneuvering? The December 19th, 2025 close Earth approach offers optimal conditions for detailed observation. At 1.8 astronomical units, about 167 million miles, that's close enough for major telescopes to collect extensive data. Spectroscopy can analyze composition changes. Photometry can precisely measure brightness and light curves. Radio observations can search for any anomalous emissions. This represents our best opportunity to characterize post-perihelion 3I Atlas. Geometrically favorable. Long observation windows. Multiple instruments across the globe able to contribute data. If anything unusual occurred during perihelion, evidence should be detectable during the December close approach. Amateur astronomers will play a crucial role here. Professional observatories have limited telescope time, allocated months in advance, not easily redirected toward new targets. But the global amateur astronomy community has thousands of sophisticated instruments operated by skilled observers who can respond quickly to interesting targets. If post-perihelion 3I Atlas shows anything unexpected, amateur data will fill gaps between professional observations, providing continuous monitoring that no single institution could achieve alone. The distributed network of backyard telescopes becomes a valuable resource for characterizing transient phenomena or detecting sporadic activity. But December observations tell only part of the story. The object continues outward, and March 16th, 2026 brings the Jupiter encounter. At 0.36 astronomical units from Jupiter, roughly 33 million miles, 3i Atlas will pass closer to the giant planet than any previous confirmed interstellar object. That proximity means Jupiter's immense gravity will noticeably alter the comet's trajectory, bending its path, increasing its velocity through a natural gravitational assist. The orbital mechanics are precise and predictable. Given 3i Atlas's approach velocity and geometry, the deflection angle and velocity change can be calculated in advance. If the actual Jupiter flyby matches predictions, that confirms our understanding of the object's mass and trajectory. Any discrepancies suggest either mass estimation errors or additional forces we haven't accounted for. Jupiter's environment also offers observational opportunities. NASA's Juno spacecraft orbits Jupiter, equipped with cameras and instruments designed to study the planet and its magnetosphere. While not optimized for comet observation, Juno might capture valuable data about 3i Atlas during close approach from a vantage point unavailable to Earth-based instruments. The Hubble Space Telescope and James Webb can also observe the Jupiter encounter, though from Earth's distance the observations will be less detailed than during the December close approach. Still, any unexpected behavior during gravitational interaction with Jupiter, anomalous trajectory changes, sudden brightness variations, deployment of secondary objects, would be scientifically explosive. After Jupiter, 3i Atlas continues its exit. By mid-2026, it will be beyond Mars' orbit, fading as it cools and recedes. By late 2026, it crosses Earth's orbital distance outbound. By 2027, it's approaching Jupiter's orbit again from the outside. Each passing month reduces observability. Distance increases, brightness fades. Solar phase angles become less favorable. The object that captured astronomical attention gradually slips back into obscurity, one more fading point of light among millions. Observation campaigns will continue as long as possible. Dedicated telescope time will track 3i Atlas through 2026 and into 2027. But eventually, it will fade below detection limits. Even Hubble and Webb have sensitivity thresholds. Once 3i Atlas becomes too faint, too distant, too embedded in background stars, we lose track permanently. The final confirmed observations might come in late 2027 or early 2028, a few last photons collected by the world's most powerful telescopes. The interstellar visitor returns to the darkness from which it came, accelerating outward, beyond Neptune, beyond the Kuiper belt, back into the realm between stars, and we're left analyzing the data we collected, synthesizing observations spanning 2 years, comparing pre-perihelion with post-perihelion characteristics, running final trajectory calculations, publishing papers that will be cited for decades. As the definitive studies of 3i Atlas, those papers will reach conclusions: natural comet, chemical composition unusual but explicable, trajectory consistent with gravitational mechanics, no evidence of artificial origin. That's the most likely outcome. That's what the scientific process will probably determine. Or the papers will be more cautious. Natural origin most likely, but certain features remain unexplained. Further study warranted if additional interstellar objects show similar characteristics. The door left slightly open, the mystery not entirely resolved, or in the scenario that would transform human civilization, the papers will present evidence that natural explanations are inadequate, that post-perihelion observations revealed features inconsistent with cometary behavior, that trajectory anomalies suggest active control, that spectroscopic analysis identified molecular patterns too specific to be random. That conclusion, if it comes, would emerge slowly. Initial papers suggesting anomalies, follow-up studies confirming or refuting those claims, heated debates in professional journals and conferences, years of analysis before consensus crystallizes. But the critical observations, the data that would drive those conclusions, all get collected in the months following perihelion. December 2025 and March 2026 are the windows that matter. If 3i Atlas reveals its nature, it will be during those periods when proximity allows detailed study, What changes after perihelion isn't just the object itself. What changes is our understanding. The transformation happens not in the comet, but in our perception of what this visitor represents. And that transformation, whether it confirms comfortable, natural explanations or forces us into uncomfortable recognition of artificiality, begins the moment 3i Atlas emerges from behind the Sun in early December, carrying whatever secrets perihelion either revealed or concealed. We wait to see what returns from that passage. We prepare instruments and train them skyward, and we hope that what we discover satisfies curiosity without triggering existential vertigo. But we suspect, perhaps, that hope might be optimistic. Let's consider a worst-case scenario that operates on a completely different scale. What if 3i Atlas isn't carrying technology, but life, panspermia, the hypothesis that life spreads between stellar systems through natural or deliberate mechanisms, has been debated since ancient Greek philosophers speculated about cosmic seeds. Modern science has given it more rigorous examination, exploring whether microorganisms could survive the harsh environment of interstellar space and whether comets or asteroids might serve as interstellar arcs. The natural version is straightforward enough in concept. Impact events on one planet, sufficiently energetic, can eject material into space at velocities exceeding escape velocities. Some percentage of that ejector might contain microorganisms from the impact site. Those organisms, encased in rock, travel through space, eventually encountering other stellar systems where gravitational capture might place them on collision courses with new planets. The survival challenges are immense. Space is cold, near absolute zero in the shadows between stars. Radiation is intense, cosmic rays and ultraviolet light that shred complex molecules. The timescales are enormous, millions of years between stellar systems even at high ejection velocities, yet research suggests certain microorganisms might survive. Bacterial spores can endure extraordinary conditions. Some organisms on Earth survive radiation doses that would kill most life forms. Given sufficient shielding within rock or ice, protected from direct radiation exposure, dormant microbes might remain viable for geological timescales. 3i Atlas, if it's a natural comet, might harbour such organisms. Not from Earth, obviously, but from whatever stellar system ejected it millions of years ago. If that system contained a planet with indigenous life, if impact or volcanic events launched material into space, if 3i Atlas formed by incorporating some of that contaminated material, then this interstellar visitor might carry alien microorganisms, frozen, dormant, but potentially viable if deposited in favourable environments. As 3i Atlas approaches perihelion, solar heating doesn't just sublime ices, it might also reactivate dormant biology. Temperature increases could trigger metabolic processes. Water sublimation could provide brief liquid medium. Organic molecules in the outgassing might include viable spores or freeze-dried cells, and all of that material gets dispersed into the solar system. Outgassing doesn't flow in one direction. Dust and gas from comet sublimation spreads into broad streams following the object's orbit. Earth might pass through those streams in subsequent years, encountering particles that originated from 3i Atlas. Most such particles would burn up in Earth's atmosphere, but some percentage, particularly smaller particles or denser materials, could survive atmospheric entry and reach the surface. This happens constantly with regular meteor showers. Material from comets and asteroids rains down on Earth continuously. If 3i Atlas carried viable organisms, some might theoretically reach Earth's environment through this mechanism. The probability for any individual organism is vanishingly small, but given billions of particles and billions of potential carriers, statistics become interesting. The deliberate panspermia variation is more unsettling. Instead of natural contamination, imagine intentional seeding. An advanced civilization that discovered microbial life or engineered it and decided to spread it throughout the galaxy. Why would they do that? Perhaps to preserve their biosphere's legacy as their civilization faced extinction. perhaps as a philosophical statement about life's cosmic significance, perhaps as practical terraforming preparation, sending microbial packages ahead of future colonization efforts, perhaps for reasons we wouldn't comprehend given completely alien value systems. Such deliberate seeding would optimize for survival. The organisms wouldn't be random microbes that happen to survive ejection. They'd be specifically chosen or engineered for durability, spore-forming species, radiation-resistant strains, organisms with repair mechanisms that can fix accumulated damage after revival. The delivery mechanism would be optimized too, not random ejection but designed dispersal. Cometary camouflage provides thermal protection during interstellar transit and delivery vehicle once the object enters target stellar systems. As perihelion heating occurs, the biological payload gets dispersed into the inner solar system where habitable planets likely exist. It's elegant in a terrible way. Use nature itself, comets that already exist and naturally visit stellar systems as Trojan horses for biological colonization. Target civilizations wouldn't recognize the threat until contamination was already established. By the time they detected unusual organisms, those organisms would have spread beyond containment. Now, before this scenario spirals into science fiction horror, let's ground it in realistic limitations. Interstellar biological contamination faces profound challenges regardless of deliberate optimization. First, compatibility. Life as we know it requires specific conditions: liquid water, appropriate temperature ranges, certain chemical elements in bioavailable forms. Alien life from a different stellar system evolved under potentially very different conditions might not be compatible with Earth's environment. Different atmospheric composition, different biochemistry, different environmental toxins. An organism perfectly adapted to its home world might find Earth lethally hostile. The oxygen content of our atmosphere would poison many conceivable biochemistries. The solar radiation spectrum differs between stars. The available nutrients don't match what alien organisms evolved to process. So even if 3I Atlas carries viable alien microorganisms, and even if some reach Earth's environment, they'd likely die quickly upon encountering conditions they're not adapted to handle, unless the organisms were specifically engineered for broad environmental tolerance. Unless they were designed to survive various planetary conditions, equipped with flexible metabolic pathways and adaptable biochemistry. But that requires technological sophistication far beyond natural selection. Second, planetary protection protocols exist precisely to prevent contamination scenarios. When we send spacecraft to other planets, particularly Mars or moons like Europa that might harbor their own life, we sterilize those spacecraft rigorously. Heat treatment, radiation exposure, chemical cleaning, all designed to minimize the risk of contaminating other worlds with Earth organisms. Would those protocols protect us from external contamination? Potentially not. They're designed to prevent outward contamination, but incoming interstellar material doesn't go through sterilization procedures. It arrives naturally, and we lack any ability to intercept or treat it before potential atmospheric entry. Third, detection. If alien microorganisms did reach Earth, would we notice? Probably eventually, but not immediately. Microbial life requires sophisticated detection methods. Novel organisms with unusual biochemistry might initially evade standard testing. They might be mistaken for known terrestrial species, especially if their basic structure resembles Earth life at superficial levels. By the time we identified alien microorganisms, if they were viable in Earth's environment, they might already be established in various ecological niches. Containment becomes nearly impossible once dispersal has occurred. The COVID-19 pandemic demonstrated how challenging it is to contain even a single infectious agent once it achieves geographic spread. An alien microorganism, particularly one that doesn't immediately cause obvious disease, and therefore goes undetected during early dispersal stages, could establish itself globally before anyone realized the threat. What kind of threat are we imagining? Not necessarily pathogenic. Most microorganisms aren't harmful to humans. The vast majority of microbial life on Earth is neutral or beneficial to human health. No reason to assume alien microbes would be specifically harmful, but ecological disruption remains possible. An organism optimized for survival across various environments might outcompete native species in certain niches. It might alter biogeochemical cycles, nitrogen fixation, carbon processing, decomposition pathways. Changes at microbial levels cascade through ecosystems in complex ways, or perhaps the organisms carry genetic material that could integrate with Earth life through horizontal gene transfer. Many bacteria naturally exchange genetic information. If alien organisms introduce novel genes into terrestrial microbes, the effects might range from negligible to transformative depending on what those genes encoded. The deliberate panspermia hypothesis assumes whoever sent the organisms intended them to integrate with local biospheres, perhaps not aggressively displacing native life, but rather adding to it, increasing complexity, introducing genetic diversity, potentially accelerating evolutionary processes toward outcomes the seeders consider desirable. From their perspective, assuming they have perspectives we can relate to at all, this might be a gift. Sharing life across the galaxy. Increasing the chances that biospheres survive and flourish, creating connections between stellar systems through shared biological heritage. From our perspective, it's an invasion, even if not harmful, even if ultimately beneficial. It's an alteration of our biosphere without consent by entities we've never communicated with, for purposes we don't understand. Could we detect biological payloads in 3i Atlas before they potentially contaminate Earth? In theory, yes, but practically, it's extraordinarily difficult. We'd need to sample the outgassing material directly, collect particles and analyze them for biological signatures. That requires spacecraft proximity missions we're not prepared to execute on short notice. Spectroscopy can identify organic molecules, and has done so for 3i Atlas, but distinguishing between abiotic organics and actual biology from a distance might be impossible. Complex organic chemistry occurs naturally in comets. Finding amino acids or nucleic acid precursors doesn't prove life, just that the raw materials exist. Direct sampling is the only way to definitively identify microorganisms. We'd need to physically collect material, return it to laboratory facilities, culture it under various conditions, examine it with microscopy and genetic sequencing. The timeline for such a mission, from concept through launch through sample return through analysis, measures in decades. 3i Atlas will be gone long before we could organize such an effort. So if panspermia is occurring, whether natural or deliberate, we're essentially helpless to prevent it. We can observe, analyze remotely, and hope that whatever happens isn't actively harmful. But we lack capacity to intercept, to sterilize, to prevent potential contamination from interstellar visitors. The worst-case panspermia scenario isn't obviously catastrophic. It's subtler than that. It's the slow realization, possibly years after 3i Atlas has departed, that novel organisms are appearing in various environments, that genetic analysis reveals sequences with no terrestrial evolutionary history, that our biosphere is changing in ways we didn't authorize and can't control, and when we trace the origins of those changes backward through time, when we model atmospheric entry timing and orbital mechanics, we find that the contamination most likely occurred during late 2025 and early 2026, when a particular interstellar comet passed through perihelion and dispersed material throughout the inner solar system. By then, it's too late for prevention, too late for containment. We're left managing consequences, studying the new organisms, trying to predict ecological impacts, and wondering whether this was natural accident or deliberate seeding by intelligences we never detected. October 29th, 2025 might mark not just perihelion, but the moment when Earth's biosphere became part of something larger. When our planet joined a network of worlds connected through shared biological material, whether we wanted that membership or not. And 3i Atlas, accelerating outward, carries whatever it carries toward the next stellar system on its trajectory, continuing a mission of dispersion that might have been ongoing for millions of years, touching countless worlds, spreading whatever form of life it harbors across the galaxy, one solar system at a time. The worst case isn't invasion, it's assimilation. Gradual, invisible, irreversible, a transformation we won't recognize until it's already complete. We should address the elephant in the observatory. When discussing potentially artificial interstellar objects, one name inevitably enters the conversation: Professor Avi Loeb of Harvard University. Loeb, chair of Harvard's astronomy department and former chair of the board on physics and astronomy of the National Academies, gained global attention with his hypothesis about Oumuamua, that strange elongated object that became the first confirmed interstellar visitor in 2017. While most astronomers concluded Oumuamua was a natural object, probably a comet or asteroid with unusual shape, Loeb argued that its properties, particularly its unexplained acceleration as it left the solar system, warranted serious consideration of artificial origin. He suggested it might be a light sail, a thin structure pushed by solar radiation, either debris from alien technology or an active probe. The response from the astronomical community was swift and largely negative. Critics argued Loeb was sensationalizing speculative interpretations while ignoring more mundane explanations. They suggested that invoking artificial origin without extraordinary evidence violated scientific principles. Several prominent astronomers publicly disputed his analysis, yet Loeb maintained his position. He didn't claim certainty that Oumuamua was artificial, only that the hypothesis deserved serious investigation rather than dismissal. He argued that science advances by examining uncomfortable possibilities, not by refusing to ask challenging questions. The controversy hasn't diminished Loeb's scientific standing in the eyes of many. He continues publishing in prestigious journals. His other research on topics ranging from black holes to early universe cosmology proceeds without controversy, but his willingness to seriously entertain artificial explanations for interstellar objects has made him a polarizing figure. Now 3I Atlas arrives, and predictably, Loeb has commented on its potential significance. He's noted the unusual chemical composition, the remarkable velocity, the convenient trajectory. He hasn't declared it artificial. He's too sophisticated a scientist to make such claims without evidence, but he's suggested that treating it as potentially artificial for purposes of analysis might be scientifically valuable. Should we dismiss his perspective as sensationalism? Or does his willingness to ask unpopular questions represent exactly the kind of intellectual courage that drives scientific progress? The tension here reflects a fundamental challenge in how science handles anomalies. Conservative interpretation protects against false positives, prevents scientists from wasting resources chasing illusory patterns, maintains the credibility of the field by avoiding extravagant claims that later prove embarrassing. But excessive conservatism risks missing genuine discoveries. If unusual observations are always explained away through increasingly contrived natural mechanisms, if artificial hypotheses are ruled out a priori regardless of evidence, then we might overlook actual contact simply because we're not psychologically prepared to recognize it. Loeb's position is that the possibility of detecting artificial objects is scientifically important enough to warrant careful investigation, even if the probability is low. He argues that the potential payoff from confirming artificial origin is so enormous that even small chances justify serious effort. It's a Bayesian calculation: multiply probability by impact magnitude to determine value of investigation. His critics counter that, without positive evidence for artificiality, assuming artificial origin is unscientific. Extraordinary claims require extraordinary evidence, as Carl Sagan famously said. And while unusual properties are interesting, they don't constitute evidence of intelligent design unless all natural explanations are exhaustively ruled out. Both positions have merit. The question is one of threshold. At what point does an accumulation of unusual characteristics justify elevated consideration of artificial hypotheses? For Oumuamua, most astronomers concluded that threshold wasn't met. Yes, It was unusual. Yes, its acceleration was initially puzzling, but subsequent analysis suggesting outgassing-based acceleration from previously undetected volatiles provided a natural explanation that most found satisfactory. Loeb disputes the adequacy of those explanations, arguing that the proposed mechanisms require specific conditions that seem unlikely. But he remains a minority position. The consensus treats Oumuamua as natural, albeit unusual. With 3I Atlas, the situation is less settled because observations are ongoing. We don't yet have complete data. Perihelion hasn't occurred. The full chemical characterization remains incomplete. So when Loeb suggests treating it as potentially artificial for analytical purposes, he's not contradicting established consensus because consensus hasn't fully formed yet. But his history with Oumuamua makes some scientists wary of his interpretations of 3I Atlas. There's concern that public attention to artificial possibilities creates sensationalism that damages astronomy's reputation and misleads the public about the actual state of evidence. Loeb counters that refusing to discuss artificial possibilities publicly creates its own problems. If evidence eventually emerges supporting artificial origin, and it turns out the scientific community has been avoiding the topic to prevent sensationalism, the public backlash would be severe. Better to acknowledge the questions honestly, explain the current evidence, and make clear what would constitute definitive answers. From the perspective of worst-case scenario analysis, Loeb's approach is actually valuable regardless of whether his specific interpretations prove correct. By seriously examining artificial hypotheses, by identifying what evidence would be required to support them, by developing testing frameworks that could distinguish natural from artificial, he's doing intellectual groundwork that becomes essential if we ever actually encounter artificial objects. Think of it as preparation. Even if 3I Atlas turns out to be entirely natural, even if every interstellar object we detect for the next century proves natural, the frameworks for analyzing potential artificial objects remain useful. They help us understand what we're looking for. They prevent us from missing genuine signals because we weren't conceptually prepared to recognize them. And if, hypothetically, 3I Atlas or some future visitor does show evidence of artificiality, having scientists who have thought seriously about such scenarios, who have published analyses and developed testing protocols, will prove invaluable. The controversy surrounding Loeb illustrates a broader tension in science between exploration and skepticism. Science requires both. Too much skepticism, and you miss discoveries. Too little, and you chase phantoms. Finding the right balance is difficult, especially with questions as emotionally charged as potential alien contact. The stakes are enormous. The public interest is intense. The temptation to either sensationalize or dismiss becomes strong depending on one's temperament and values. Perhaps the healthiest approach is plurality. Let some scientists like Loeb seriously explore artificial hypotheses and develop rigorous frameworks for testing them. Let others focus on exhaustively characterizing natural explanations and identifying where our understanding of cometary behavior might be incomplete. Both approaches contribute value. The scientific literature can accommodate both perspectives. Papers arguing for natural origin and papers examining artificial possibilities can coexist, both subject to peer review, both required to meet evidential standards. The discourse remains productive as long as it remains grounded in observation rather than speculation for its own sake. What's important is that the questions get asked, whether 3I Atlas is natural or artificial, whether Oumuamua was a comet or a light sail. The fact that interstellar objects raise these questions is scientifically valuable. They force us to examine our assumptions, to clarify what we actually know versus what we assume, to develop better tools and methods for distinguishing between competing hypotheses. Loeb's willingness to publicly entertain artificial explanations makes him controversial. But controversy itself can be productive if it drives more rigorous analysis and clearer thinking about what evidence actually tells us. October 29th, 2025 approaches, regardless of academic debates. 3I Atlas will reach perihelion. Whether astronomers agree on how to interpret its properties, the observations will occur, the data will be collected, and eventually consensus will form based on what that data reveals. If that consensus concludes natural origin, Loeb will be seen as provocative but ultimately wrong in his elevated concern about artificial possibilities. If that consensus concludes artificial origin, he'll be recognized as ahead of his field in recognizing the implications of unusual observations. But either way, the questions he's helped bring into mainstream astronomical discourse, questions about how we recognize intelligence beyond Earth, about what artificial objects might look like, about whether we're prepared to detect them if they exist, those questions remain valuable, independent of any specific object, and that might be the most important contribution of controversial figures in science. Not necessarily being right about specific claims, but rather forcing their fields to think more broadly, to question comfortable assumptions, to prepare for possibilities that seem unlikely but carry enormous significance if they occur. As we watch 3I Atlas approach perihelion, we can appreciate both the skeptics who demand rigorous natural explanations and the explorers who wonder whether we're witnessing something unprecedented, because worst-case analysis requires considering both possibilities, that we're so eager to find aliens we see them everywhere, and that we're so committed to natural explanations we might miss them entirely. 3. Atlas is notable partially because it's rare. In all of human history, we've confirmed only 3 interstellar objects: Oumuamua in 2017, 2I/Borisov in 2019, and now this visitor, 3 objects across 8 years. That rarity contributes to their fascination, but rarity is about to end. The Vera Rubin Observatory, currently in final stages of construction in Chile, will revolutionize our ability to detect transient astronomical phenomena. Vera Rubin will survey the entire visible sky every few nights, generating unprecedented volumes of data about anything that moves or changes. Its wide-field camera and rapid survey cadence are optimized for exactly the kind of detection work that identified our 3 known interstellar visitors. Astronomers predict Vera Rubin will detect dozens, perhaps hundreds of interstellar objects per year once it reaches full operational capacity. What has been rare will become routine. What has been special will become statistical. And with that transition, we'll face a new challenge. How do we respond to frequent interstellar visitations when we can barely manage to study the rare ones we've encountered so far? Consider the timeline for 3I Atlas. Discovery to perihelion spans months. Observation campaigns require coordinating multiple facilities. Spectroscopic analysis takes time. Trajectory calculations require tracking over extended periods. Peer review and publication of findings happens on timescales of months to years. Now, imagine dealing with dozens of such objects simultaneously, each requiring observation time on the same limited set of powerful telescopes, each demanding spectroscopic analysis, each potentially harboring unusual characteristics that warrant detailed investigation. We lack capacity to study them all thoroughly. Choices become necessary. Which interstellar visitors merit intensive study, which can be catalogued minimally and set aside? How do we identify the genuinely unusual among many unusual objects? And if the worst-case scenarios we've been exploring have any validity, if some small fraction of interstellar objects are actually artificial, how do we avoid missing the significant ones amid the noise of routine detections? The problem resembles challenges in other domains. Security services face similar issues: thousands of potential threats, limited resources for investigation, need to identify the genuine dangers without wasting effort on false alarms. Medical screening deals with comparable statistics: large populations, rare diseases, balancing sensitivity against specificity. But those fields have decades or centuries of experience developing triage systems and risk assessment frameworks. Interstellar object analysis is brand new. We've studied 3 examples total. We have no robust statistics on what constitutes normal versus anomalous. We're essentially making it up as we go. The vulnerability isn't just about detection, It's about response capacity. Even if we detect something genuinely unusual, what can we actually do about it? 3I Atlas illustrates the problem. Moving at 130,000 miles per hour, it will transit the inner solar system in months. If we wanted to send a spacecraft to intercept it, to conduct close-up observations or sample collection, we'd need to launch on extremely short notice with mission designs we haven't prepared. Our fastest spacecraft, New Horizons, took almost a decade to reach Pluto. Parker Solar Probe achieves high velocities using multiple gravitational assists over years. Neither mission architecture works for intercepting fast-moving interstellar objects with brief solar system transit times. We could potentially develop rapid response spacecraft designed specifically for interstellar visitor intercepts, kept in storage, ready for quick launch when interesting targets appear. But such missions would be expensive, would need to remain on standby potentially for years, and face enormous technical challenges, matching velocities with objects moving far faster than typical solar system bodies. No space agency has budgeted for such capabilities. No mission architecture exists beyond preliminary concept studies. If 3I Atlas turned out to be obviously artificial tomorrow, we'd have no realistic capability to reach it before it exits the solar system. That helplessness defines our vulnerability. We can observe from a distance. We can analyze spectroscopy and photometry. We can track trajectories and model compositions, but actual physical interaction, sampling or examination or contact remains beyond our current capabilities for fast-moving interstellar objects. It's like watching something incredibly important pass by your window while being unable to open the door. The communication challenge adds another dimension. If an interstellar object were confirmed artificial and we wanted to attempt communication, we'd face technical and political obstacles. Technically, we have powerful radio transmitters. The Arecibo Observatory, before its collapse, could have transmitted toward 3I Atlas. Other facilities, the Deep Space Network, various military and commercial installations have sufficient power. The signals would reach an object at 1.36 AU in minutes. Who decides content? In what format? Using what encoding scheme? And assuming signals are transmitted, how long do we listen for responses? Days? Weeks? At what frequencies? These questions have no established answers. SETI High has developed protocols for potential radio contact, but those assume bidirectional communication with distant civilizations, not messages to objects passing through our immediate neighborhood. And politically, the question of whether to transmit at all remains contentious. Active SETI, deliberately announcing our presence to potential alien intelligence, has vocal opponents who argue that we should remain silent until we better understand the risks. If an interstellar visitor were confirmed artificial, that debate would become urgent and unavoidable. Some would demand immediate communication attempts. Others would counsel caution. National security establishments might want control over any transmissions. International coordination would be essential but difficult to achieve quickly. All while the object recedes at thousands of miles per second, the communication window gradually closing. Our vulnerability extends beyond individual objects to the broader question of whether interstellar space is more active than we've realized. Oumuamua showed characteristics suggesting it might be a fragment rather than an intact object. If large interstellar bodies occasionally fracture, the galaxy might be full of debris clouds, diffuse swarms of smaller objects, difficult to detect individually, but potentially hazardous collectively. We wouldn't necessarily notice such debris until we flew through it, either with robotic spacecraft or eventually with crewed missions to the outer solar system. The collision risk might be minimal given the vastness of space, but the uncertainty itself is troubling. And if deliberate surveillance or panspermia scenarios have any validity, if the galaxy contains networks of artificial objects disguised as natural phenomena, our current detection capabilities and analysis frameworks are woefully inadequate to recognize them. We're essentially cosmic children, just beginning to notice that our solar system isn't isolated, that visitors arrive from elsewhere, that the space between stars contains traffic we've only recently become sophisticated enough to detect. And like children, we lack the wisdom, capabilities, and coordination to respond effectively to what we're discovering. We're reactive rather than proactive, surprised by each new detection rather than prepared for routine interstellar traffic, dependent on luck and timing rather than systematic monitoring. Vera Rubin will improve detection, but detection alone doesn't solve the broader vulnerability. We'll see more objects but remain unable to study them thoroughly or interact with them physically. We'll accumulate statistics but lack capacity to investigate individual cases in depth. It's a strange position to occupy. Technologically sophisticated enough to detect interstellar visitors, not sophisticated enough to truly understand or engage with them. Advanced enough to ask profound questions, not advanced enough to answer them definitively. October 29th, 2025 marks one object's perihelion passage, but it also represents a moment in humanity's broader awakening to the reality that our solar system is permeable, that the galaxy occasionally reaches in and touches us through wandering objects, that we live in a more connected cosmos than previous generations imagined. And we're vulnerable because connection implies risks. We're only beginning to comprehend, not necessarily hostile risks, but the risks that come with limited understanding and insufficient capability when encountering phenomena beyond our experience. 3i Atlas will pass. Others will come. And gradually, through accumulated observation and hard-won experience, we'll develop better frameworks for understanding what visits us and what it might mean. But right now, in 2024, approaching the perihelion passage of our third confirmed interstellar visitor, we remain fundamentally vulnerable to the implications of what we're observing. And the worst case isn't that something catastrophic arrives. The worst case is that something significant arrives, and we lack the wisdom or capability to recognize its significance before the opportunity to investigate passes forever. Let's step back from 3i Atlas specifically and examine the broader context. 3 confirmed interstellar objects, all apparently natural, no obvious signs of artificiality despite intensive scrutiny. What does that tell us? The optimistic interpretation is simple. Interstellar objects are natural phenomena. Comets and asteroids get ejected from stellar systems through gravitational interactions. They wander the galaxy for millions of years. Occasionally they pass through other stellar systems. We're finally detecting them because our telescopes have become sophisticated enough. Mystery solved, but the Fermi paradox complicates that comfortable conclusion. Enrico Fermi famously asked if the galaxy is vast, ancient, and likely home to many technological civilizations, where are they? Why do we see no evidence of intelligence despite decades of searching? Various solutions have been proposed. Perhaps intelligence is extremely rare. Perhaps faster than light travel is impossible and interstellar distances prevent expansion. Perhaps advanced civilizations deliberately avoid contact. Perhaps they exist but are so different from us that we don't recognize their signatures. Perhaps the Great Filter prevents civilizations from surviving long enough to become observable. Or perhaps they're here, have been here, and we simply haven't recognized the evidence. 3i Atlas and its fellow interstellar visitors fit into this puzzle in intriguing ways. If the galaxy contains numerous spacefaring civilizations, wouldn't at least some of them send interstellar probes? Wouldn't exploration and reconnaissance be common activities for technological species? Yet we've detected 3 interstellar objects, and all 3 appear natural. No obvious technology, no clear signals, nothing that screams intelligent design despite our increasingly sophisticated analysis. That could mean intelligence is rare or non-existent. The galaxy might be essentially empty of other technological civilizations, making us the only observers in our region of space. Or it could mean that intelligence disguises its activities extremely well, that probes are designed to look natural specifically to avoid detection by primitive civilizations like ours, that the objects we're categorizing as natural comets and asteroids might include some fraction of artificial observers that have passed our scrutiny. The dark forest hypothesis, popularized by Lusick's science fiction trilogy but rooted in game theory, suggests that civilizations remain silent because announcing your presence carries existential risk. In a universe where intentions are unknowable and technology could represent threat, the safest strategy might be hiding. If dark forest logic governs galactic civilization, we wouldn't expect obvious artificial objects. We'd expect camouflage, stealth, observation without announcement. Natural appearing probes would be exactly what reconnaissance would look like. But this reasoning can become unfalsifiable. If everything natural could potentially be artificial in disguise, if lack of obvious technology becomes evidence for sophisticated technology, we've created a hypothesis that can't be tested. That's not science, that's paranoia. So we need boundaries. We should seriously consider artificial explanations when evidence supports them, but we can't treat every unusual characteristic as proof of intelligence. Most unusual things are natural. The universe is vast and diverse enough that rare phenomena occur through pure statistics. The silence of the galaxy remains disturbing regardless of how we interpret it. 3 interstellar objects is a tiny sample size. Dozens more detections from Vera Rubin will improve statistics. Hundreds of observations over the next decade will tell us whether certain characteristics cluster in ways suggesting multiple categories of objects. If all interstellar visitors continue to appear natural, with variations explicable through different formation conditions and chemical environments, the natural interpretation becomes increasingly robust. But if patterns emerge, if some subset of objects shows correlated unusual characteristics, if statistical analysis suggests non-random distributions, then questions about potential artificiality become more pressing. 3I Atlas might be that statistical outlier that hints at deeper patterns, or it might simply be at the extreme end of natural variation. We won't know until we have sufficient data to judge whether it's genuinely anomalous or just the first example we've studied of a particular type of natural object. The philosophical weight of the silence is what makes the Fermi paradox so troubling. The galaxy is approximately 13.6 billion years old. Earth is 4.5 billion years old. If intelligent life arises on even a small fraction of suitable planets, and if some of those civilizations survive for geological timescales, the galaxy should be teeming with evidence of intelligence. Yet we see nothing obvious. No megastructures, no clear signals, no interference with our development, just silence. That silence suggests either we're rare, or intelligence tends toward outcomes that don't produce observable signatures across interstellar distances, or we're looking in wrong places using wrong assumptions about what intelligence looks like. 3I Atlas passes through that silence, a wanderer from elsewhere carrying whatever it carries, observed by our instruments but remaining fundamentally enigmatic. And perhaps that's the answer to Fermi. Perhaps the galaxy is full of enigmas, objects and phenomena that could be natural or artificial but remain ambiguous to any observer who lacks the sophistication to distinguish between those possibilities. Perhaps intelligence leaves subtle signatures, hints, and suggestions rather than obvious monuments. Perhaps the universe is whispering, and we're listening for shouts. Or perhaps we're simply alone, the only witnesses in this region of space, and all the objects passing through are exactly what they appear to be: cosmic debris, fragments of stellar systems, natural phenomena worthy of scientific study but carrying no deeper implications. The uncertainty is maddening, but it's also honest. We don't know. We lack sufficient data to answer fundamental questions about intelligence in the universe. We're doing our best with limited capabilities and incomplete information. October 29th, 2025 won't resolve the Fermi paradox. 3I Atlas won't definitively answer whether we're alone, but it represents another data point, another opportunity to refine our understanding, another chance to test our assumptions about what passes through the darkness. And the silence continues, neither confirming our solitude nor promising companionship, simply being what it is, the vast quiet cosmos that contains us, that occasionally sends visitors, that keeps its deepest secrets while we gradually, painstakingly, try to learn how to listen. The worst-case interpretation of the silence is that it's not absence, but discretion, not emptiness, but careful observation by entities who have reasons for remaining hidden. And we'll never know the difference until we become sophisticated enough to recognize subtlety, to detect camouflage, to understand that silence itself can be a form of communication from intelligences patient enough to wait for us to develop the wisdom to comprehend what they're not saying. We've explored worst-case scenarios, contemplated artificial probes and deliberate panspermia, examined trajectories and chemical signatures for hints of intelligence. Now we need to ground all that speculation in what observations actually reveal. The data from 3i Atlas, as of late 2024, supports natural origin. Let's be clear and honest about that. Hubble Space Telescope observations show an object consistent with cometary size estimates between 1 and 3 kilometers diameter. The brightness and light curve match expectations for a rotating nucleus with irregular shape, typical of comets. No obvious anomalies in the photometric data. James Webb Space Telescope spectroscopy detected the unusual CO5 to water ratio that we've discussed extensively. But unusual isn't impossible. JWST also identified various other molecules, carbon monoxide, possibly methane, organic compounds. The spectrum is consistent with an object formed in a chemically different environment than our solar system, but still within the range of possible natural compositions. Trajectory calculations from multiple observatories worldwide show paths consistent with gravitational mechanics, plus non-gravitational forces from outgassing. The magnitude of those forces aligns with estimates based on observed activity levels. No anomalous accelerations requiring exotic explanations. Ground-based observations from facilities in Chile, Hawaii, and elsewhere have tracked 3i Atlas over months, building detailed light curves and monitoring activity levels. The variations detected correspond to expected rotational modulation and increasing solar heating. Again, nothing obviously inconsistent with natural cometary behavior. Mars orbiters will provide additional data during perihelion, though with limitations we've discussed, but their planned observations aim to characterize outgassing and brightness changes during closest solar approach. The observation protocols are designed for natural phenomena, so the scientific consensus, to the extent one has formed, treats 3i Atlas as a natural interstellar comet with somewhat unusual but not inexplicable chemical composition. The unusual characteristics, the high velocity, the CO5 dominance, the trajectory geometry, all have been examined and found to have plausible natural explanations. None of the observations require invoking artificial origin. Could those observations be consistent with artificial origin? Yes, if the hypothetical artificial object is designed to mimic natural behavior. But consistency isn't evidence. Many hypotheses can be consistent with the same data. Science requires choosing explanations based on probability and simplicity, and natural origin is both more probable and simpler. Extraordinary claims require extraordinary evidence. Carl Sagan's principle applies here. Claiming artificial origin for 3i Atlas would be extraordinary. The evidence would need to be commensurately strong, unambiguous technological signatures, impossible chemical combinations, trajectory changes inconsistent with any natural forces, deliberate signaling. We have none of that. We have unusual chemistry that's surprising but not impossible. We have a convenient trajectory that could be coincidental. We have high velocity that requires long travel times, but not advanced propulsion. None of that reaches the threshold for claiming artificial origin. Not even close. And that's appropriate. Scientific conservatism protects against false conclusions. Most unusual observations turn out to have mundane explanations once we understand them better. Jumping to exotic interpretations prematurely wastes resources and damages credibility. So why have we spent thousands of words exploring worst-case scenarios if the data doesn't support them? Because worst-case analysis isn't the same as most likely analysis. It's about examining possibilities that, while improbable, carry sufficient importance to warrant consideration. It's about asking if we're wrong about natural origin. What would that mean? What should we be watching for? What observations might change our interpretation? How would we recognize artificial origin if it existed? Those questions have value, even if 3i Atlas proves entirely natural. They prepare us for future observations. They clarify what evidence would actually be required to support extraordinary claims. They force us to examine our assumptions and understand why we believe what we believe. And they acknowledge uncertainty. Honestly, the fact that natural origin is most likely doesn't mean it's certain. We're making inferences based on limited data. We're applying frameworks developed from studying solar system objects to an interstellar visitor formed under completely different conditions. Could those frameworks be incomplete? Could we be missing something because we don't know what to look for? Possibly. That's not an argument for abandoning scientific consensus. It's recognition that knowledge is provisional, that observations continue, that our understanding improves as we gather more data. The December 2025 post-perihelion observations will be crucial. If 3i Atlas emerges behaving exactly as models predict, natural origin becomes even more strongly supported. If unexpected changes appear, questions multiply, but most likely it will behave naturally. Most likely, the full data set collected through 2026 will support the conclusion that we observed an interesting but ultimately natural comet from interstellar space. And that's fine. That's still valuable scientifically. Learning about chemical diversity in comets formed around other stars teaches us about planet formation and stellar system evolution. Understanding how objects survive millions of years in interstellar space informs models of galactic material cycling. Improving our detection and analysis capabilities prepares us for the dozens of additional interstellar visitors Vera Rubin will discover. Natural phenomena are worthy of study. Not everything needs to be artificial to be important. The worst-case scenarios we've explored remain valuable as thought experiments, even if they don't apply to 3i Atlas. Because someday, perhaps with this object, or perhaps with one of the many future interstellar visitors, we might encounter something that doesn't fit natural frameworks. And when that day comes, if it comes, the intellectual groundwork laid by examining worst-case scenarios, even speculative ones, will prove essential for recognizing and properly analyzing genuinely anomalous observations. For now, the data tells us 3i Atlas is most likely a natural interstellar comet, unusual in some respects, but explicable through natural processes. Worthy of continued observation and analysis, but not requiring exotic explanations, science demands we follow the data where it leads, not where speculation takes us. And currently, the data leads toward natural origin. October 29th, 2025 will come and go. 3i Atlas will round the sun, heat up, outgas vigorously and begin its departure. We'll observe as much as solar conjunction permits. We'll analyze what we collect, and most likely we'll confirm that nature remains far more interesting than we need artificial constructs to create wonder. But we'll watch carefully. We'll check our assumptions. We'll remain open to evidence that might challenge comfortable conclusions, because that's what science is. Systematic skepticism balanced with intellectual honesty. Trust the data. Question assumptions. Follow evidence. Remain prepared for surprises, and acknowledge that the universe has surprised us before and will undoubtedly do so again. October 29th, 2025 passes into history. Perihelion occurs behind the solar glare, unobserved but calculated with precision. The mathematics assure us that 3i Atlas reached closest approach, experienced maximum solar heating, and began its long acceleration outward. December brings renewed visibility. Observatories train instruments on the predicted coordinates. First images arrive, processed, analyzed, compared against expectations. The object behaves as models forecast. Nature validates our understanding once again. Weeks become months. 3i Atlas continues its journey through the inner solar system. The December 19th close Earth approach offers excellent observation opportunities. Spectra confirm chemical composition. Photometry tracks brightness variations. Astrometry plots trajectory with increasing accuracy. Everything fits. All the data supports natural origin. The unusual chemistry remains unusual but explicable. The high velocity reflects its interstellar origin, but requires no exotic propulsion. The trajectory follows gravitational mechanics, plus standard outgassing forces. March 16, 2026 arrives, and 3I Atlas threads through Jupiter's gravitational domain, passing within 33 million miles of the giant planet. The trajectory bends precisely as Newtonian mechanics predicts. Jupiter's gravity provides a final boost, increasing outbound velocity, sending this visitor back toward interstellar space faster than it arrived, and then the long fade begins. Throughout 2026 and into 2027, 3I Atlas recedes, brightness diminishes. Activity decreases as it cools, observation becomes increasingly challenging as the object weakens and distance grows. Final confirmed detections come in late 2027. A few last photons collected by humanity's most powerful telescopes. The final data points added to an ever-growing database. Then silence as 3I Atlas drops below detection thresholds. It continues onward, of course. The silence is ours, not its. The object that captured our attention for 2 years proceeds on its trajectory, accelerating away from the sun, climbing back toward the velocities it held during its millions of years of wandering before encountering our stellar system. Within a decade, it will be farther from the sun than any human spacecraft has traveled. Within a century, it will have left the region where the sun's influence dominates. Within a few thousand years, it will be light years away, approaching other stellar systems on a journey that might continue for billions of years more, and we'll remember it. Papers will be published, analyzing the complete data set. Graduate students decades from now will write dissertations examining aspects of 3I Atlas we didn't fully explore. The comet will become a reference point, the third confirmed interstellar visitor, a benchmark against which future discoveries are compared. But beyond the data, beyond the scientific papers and academic discussions, what has 3I Atlas taught us? It's taught us humility. Despite our sophisticated instruments and theoretical frameworks, we faced genuine uncertainty about an object passing through our immediate neighborhood. We couldn't say with absolute certainty whether it was natural or artificial. We had to make judgments based on probability and inference. Acknowledging that certainty remained elusive, it's taught us preparedness matters. The next interstellar visitor, and there will be many, will arrive on its own schedule. We either have observational capabilities and analysis frameworks ready, or we miss opportunities. Preparation determines what we learn. It's taught us that the universe is more connected than we imagined. Interstellar space isn't empty void, but a medium through which material cycles. Objects from distant stellar systems pass through ours. Presumably our own material, ejected through gravitational interactions, wanders the galaxy visiting other systems. We're part of a vast ecological network of stellar systems exchanging material across light years. It's taught us that rarity is changing. 3 confirmed interstellar objects sounds rare, but with Vera Rubin coming online, dozens per year becomes routine. What has been exceptional will be ordinary. And with that transition, we need new frameworks for managing and prioritizing observations. Most importantly, 3I Atlas has taught us to balance wonder with rigor. It's natural to see a visitor from interstellar space and imagine possibilities beyond the mundane. Intelligence, messages, panspermia, all capture imagination in ways that natural phenomena sometimes don't, but imagination must be balanced with evidence. Wonder is valuable, but it shouldn't override careful analysis. We can simultaneously appreciate the profound nature of interstellar visitors while subjecting them to rigorous scientific scrutiny. The speculation we've explored in this examination, worst-case scenarios ranging from surveillance probes to biological contamination to ancient relics of extinct civilizations, these serve a purpose beyond entertainment. They clarify what's possible versus what's probable. They identify what evidence would be required to support extraordinary claims. They prepare our thinking for potential future discoveries, but they remain speculation. The data suggests 3i Atlas is natural, and we should accept that conclusion while remaining open to future evidence that might challenge it. As this visitor recedes beyond our observation, it carries with it the hope that humanity is maturing in its relationship with the cosmos. We're moving past the initial shock of discovering that interstellar visitors exist. We're developing protocols and capabilities for studying them. We're asking better questions and building better tools for finding answers. The galaxy is vast. The universe is ancient. We've existed as technological civilization for barely a century. We've been capable of detecting interstellar objects for less than a decade. We're infants in cosmic terms, just opening our eyes to the reality that surrounds us. 3i Atlas is a teacher, whether it's a frozen chunk of ice and rock or something more exotic. It teaches through its presence, through the questions it raises, through the observations it enables, through the intellectual challenges it presents, and as it departs, accelerating back into the darkness from which it came, we're left richer for having witnessed its passage. We know more about cometary diversity. We understand better how to detect and track fast-moving objects. We've tested our observational capabilities and identified areas needing improvement. We've also been reminded of our place. We are observers on one small planet in one ordinary solar system in one arm of one galaxy among trillions. We don't control what visits us. We can only watch, learn, and try to understand. It tempers the arrogance that sometimes accompanies technological advancement. It reminds us that the universe operates on scales and timelines far beyond human significance. It teaches patience and perspective. Someday, perhaps soon, with Vera Rubin's help, we'll detect an interstellar visitor that doesn't fit natural frameworks as comfortably as 3i Atlas does. We'll encounter something genuinely anomalous, something that forces us to seriously entertain artificial explanations because natural ones become increasingly untenable. When that day comes, the experience we've gained from studying Oumuamua, 2i/Borisov, and 3i Atlas will prove invaluable. We'll have baseline understanding of what natural interstellar objects look like. We'll have frameworks for distinguishing unusual but natural from impossible if natural. We'll be prepared, as much as we can be, for the profound discovery that we're not alone, or perhaps we'll study dozens, then hundreds, then thousands of interstellar visitors and find that all of them, every single one, fits natural frameworks. Perhaps the galaxy is quieter than we hoped. Perhaps intelligence is rarer than we imagined. Perhaps we are, in this region of space at this point in cosmic history, alone with our questions. Either answer is scientifically valuable. Either answer teaches us about the universe we inhabit. As 3i Atlas fades from view, as 2027 turns to 2028, and the last detections become historical footnotes, we turn our attention to what comes next. More visitors will arrive, more mysteries will present themselves, more opportunities to learn will emerge, and we'll face them with the knowledge gained from this encounter. We'll be better observers, better analysts, better prepared to extract maximum scientific value from brief transits through our solar system. Thank you, 3i Atlas, for visiting. Thank you for the questions you raised and the data you provided. Thank you for reminding us that the cosmos is vast and full of wonders worth studying. Safe travels on your journey through the galaxy. May you visit other stellar systems with equal generosity, offering other potential observers the same opportunities for learning that you've given us. And may we, as a civilization, continue growing in wisdom and capability, so that when the next messenger arrives, whether from nature or from intelligence we've yet to encounter, we're ready to receive what it has to teach. October 29th, 2025 marked a perihelion. But more than that, it marked a moment in humanity's ongoing awakening to the reality that we live in a galaxy full of wanderers, that isolation is illusion, that the space between stars carries traffic we're only beginning to detect and understand. 3i Atlas leaves us changed. Not because it was artificial, Probably it wasn't. Not because it carried messages, almost certainly it didn't, but because it was here, because we saw it, because we tried to understand it. And in that trying, in that reaching toward comprehension of something that came from elsewhere, we became a little more cosmic ourselves, a little more aware of the vast darkness that contains us, a little more humble about our place, a little more prepared for whatever visits us next. Farewell, wanderer. Thank you for the journey we've shared across these months of observation and wonder. The data you've given us will be studied for decades. The questions you've raised will shape how we think about future visitors, and somewhere millions of years from now, you'll enter another stellar system, pass another star, perhaps encounter another civilization just beginning to develop the capability to notice you. And they'll wonder, as we have wondered, what you are and where you've been and what secrets you might carry, and you'll pass through their system as you've passed through ours, neither confirming nor denying their speculations, simply being what you are, a messenger from the cosmic depths, carrying evidence that the galaxy is far more interconnected than any of us fully comprehend. Safe journey, clear skies, and thank you for everything you've taught us about the universe and about ourselves.